Hi, this is complete lesson in Edexcel IAL Physics Unit 3. See the description of this video. All the useful links are given in the description of this video. Also, by using the playlist of this channel, you can navigate to any lessons related to any unit. In the playlist, all my videos, I think there are around 150, more than 150 videos, are grouped in different titles. Say for example, Mechanics, Mathematics M1, Mechanics, Mathematics M2, Mechanics, Mathematics M3, then in Physics, Unit 1 lessons, Unit 1 past paper discussions, Unit 2 lessons, Unit 2 past paper discussions, and so on. Like that, in playlist I grouped all my videos in different titles. So by using the playlist, you can navigate to any lessons you want to watch, either in Physics or Mathematics, Mechanics. Okay, so this unit, that is Unit 3, is called Practical Skills in Physics. So the questions based on Unit 3 are mostly focused on practical skills. The practicals what they ask could be a new practical. They will guide you in the exam paper. They'll give you the description of the practical. So don't expect the questions related to practicals only from your syllabus. There could be new practical questions also could be there. It came in the past paper. For example, I think June 2024 paper, there's a question about finding the resistivity of a wire in the form of loop. Then there's another question like that. Some other questions came in somewhere October 2022 also. So like that, they can ask any questions based on practicals, but the guidance will be there. They'll give you the guidance and the information related to practicals, so it won't be hard. You can just manage depending on the data and the guidance they give. Okay, so first, these practicals means we do measurements, is it? Most of the practicals we take measurements, whether it's physics or biology or chemistry. There could be measurements during our practical. Okay, so to do measurements or to take some measurements, we must use an instrument. Without instruments, we can't take any measurements. So when we consider an instrument, there's a technical word we use that is called resolution of the instrument or least count of the instrument. First, you must know that resolution or least count. Or resolution. Okay, so least count or resolution of the instrument, what do you mean by that? The minimum value that could be recorded by the given instrument. The minimum quantity that could be measured by the instrument is called least count of the instrument. You must know the least count of certain instruments. For example, when you think about a meter rule or ruler, the minimum measurement that could be measured, or minimum value that could be measured by using meter rule is 1 millimeter. You can see the smallest division shown in meter rule is 1 millimeter. So for meter rule, that is 1 millimeter is the least count or resolution. Same way, you would have used vernier caliper. Vernier caliper, the minimum thickness or minimum value that could be measured by using vernier caliper is 0.1 millimeter. That is 0.1 millimeter. Same way for micrometer screw gauge. That is 0.01 millimeter. A protractor, normally what we use protractor, that is 1 degree. Protractor 1 degree. These are the standard instruments you must remember. Other than that, say for example, sometimes they won't tell the least count. These least counts you must know, you must remember that. But sometimes they might give a question, weighing scale records something like weight is equal to 2.46 grams. Okay, what could be the least count of this weighing scale? The smallest value that could be measured by this weighing scale is given in 2 decimal points. So for this weighing scale, least count will be 0.01 gram. It's 2 decimal points. So the smallest measurement that could be recorded by this particular weighing scale is 0.01 grams. Okay. Sometimes we might use we might use a weight slots to apply force in certain experiments, something like weight slots might be used to apply force. For example, some experiment like a glider or maybe a trolley. You need to measure the force and the acceleration. So there's a pulley. Through the pulley, a string is applied, connected, and there you might hang weight slots. So imagine if you are using 50 gram weight slots. That means 50 gram weight slots means 50 gram, 100 gram, 150, 200, 250 grams, like that you can add to this hanger, right? So there the tension provides the required accelerator force for the acceleration of the trolley. If the trolley is accelerating, anyway, whatever it is, the required force is provided by the weight slots. Okay, so here the smallest force that could be obtained, or the smallest force that could be measured by using this setup. You are not using any Newton meter or anything. The force is applied just by using the weight slots. So the smallest force, that is the least count of the force in this experiment, or the resolution of the force in this experiment. So the smallest force is 50 gram. 50 gram. Normally we don't give the force in grams, so you need to convert this to Newton. 50 gram divided by 1000 to convert to kilogram, 9.81 Newton. So if you solve it, you will get 0.49 Newton. So this is the least count or resolution of the force applied to the trolley in this particular experiment. So the least count means the minimum force that could be, minimum quantity that could be measured by an instrument. But here the instrument that we use to apply force is weight slot. So the least count of the force is 0.49 Newton. So what I told, least count is true for all the instruments where we take measurements. It's true in biology or chemistry also. Any instrument, even for pipette, there's a least count. Even for measuring cylinder, there's a least count. Even for beaker, if you are using a beaker to measure the volume, there is least count. Okay. So the least count is something related to the instrument that we are using. Okay, the next thing is uncertainty. Your teachers would have told that about uncertainty of a measurement. Okay, uncertainty of a measurement. Measurements have uncertainty. Uncertainty of a measurement. Careful, I'm talking about a measurement. Each measurement or each and every measurement is not sure. That means whatever the value you record is not correct. I'm not saying it's correct. It has a range. Why is it like that? I can explain by using simple experiment, the idea of the uncertainty. Imagine you are trying to measure a voltage in a circuit, something like there's a circuit, right? There's a EMF. I'm not interested about that EMF, but there are two resistors are connected. This resistance is R1. There's a next resistor, its resistance is R2, right? You have to measure the both resistance R1 and R2. So you are connecting two different ideal voltmeters. Ideal voltmeter. You can see my unit 2 lessons in electricity. There I had a separate topic, I think, about voltmeters and ammeters. So ideal voltmeter means its internal resistance is infinity. The current flow through is negligible. So it reads a perfectly correct voltage, right? So voltmeter is connected across this one. A voltmeter is connected across this one. and the same identical voltmeter and ideal voltmeter is connected across R2 also. So there are two different voltmeters, both are ideals. There is no mistake in the voltmeters, they are perfectly accurate voltmeters. They are connected across the two resistors, those are connected in series, and the two voltmeters records 2.6 volt, this reads 2.6 volt, this also reads 2.6 volt. So according to this circuit experiment, you know R1 and R2 are connected in series and both voltmeters are ideal, means no current flow through the voltmeter. So whatever the current comes from the cell will flow through both resistors. The same current will flow through both resistors. They have the same voltage also. The voltmeters are recording the same voltage mean according to V equal IR. So at the end of the experiment, the student will conclude, since both have the same current through them and the voltmeters are ideal, no current flow through the voltmeters, and the voltmeter readings are the same, 2.6. That means both resistors R1 and R2 are both have the same resistance. So R1 of resistance R1 will be equal to R2. That will be the conclusion the student will say at the end of the experiment. So the student will conclude both resistors have the same resistance. Okay, now the same resistors are now connected, the same circuit I am drawing again, but I am going to use another two different types of ideal voltmeters like this. So here the same circuit I am drawing again, but the same circuit, the same two resistors are there, R1, R2. R1, R2. So now you are connecting another two ideal voltmeters, another two ideal voltmeters. So these are also correct, perfectly correct voltmeters, ideal voltmeters. There are no mistakes, but the thing is these two voltmeters can record voltage in 2 decimal points. Here the two voltmeters are ideal and there are no mistakes, but they record in 1 decimal point. But these two voltmeters are ideal, that means there is no current flow through them, but they can record in 2 decimal points. So the same current is flowing here also. So when you connect these two voltmeters, they are reading this voltmeter which is connected across R1, that voltmeter is recording 2.55 volt, and this voltmeter which is connected across R2 is recording 2.64 volt. Okay, now look at here. You know, if you approximate this to 1 decimal point, because this voltmeter can record only 1 decimal point, if you approximate this to 1 decimal point, it will be 2.6. When you approximate this to 1 decimal point, 2.6. That's the reason these two voltmeters recorded 2.6, 2.6, and the student concluded both R1 and R2 have the same resistance. Now, after connecting two different ideal voltmeters, they can record, those can record in 2 decimal points. Now we know that this resistance has greater voltage than this. The same current is flowing through them. So that means R2 greater than R1. See, the conclusion has changed. So by using 1 decimal points, I concluded R1 equal R2. But when I use the same circuit, same power supply, nothing different, everything same. But only the voltmeters also ideal. They don't have any mistake. But only the decimal points are different. They can record in 1 decimal point. The resolution is 0.1. Here the resolution is 0.01. So when I use 0.01 resolution voltmeter, we know that R2 greater than R1, the reason the voltage across it is going to be 2.64. That means if the voltage, if the voltage from 2.55 volt to 2.64 volt, the voltmeter which can record in 1 decimal point is going to read 2.6 volt. See? So there is a range from 2.55 to 2.64. It's reading 2.6. Right? So if you are reading 2.6, if you are getting 2.6, I can say I am not accepting that, because I don't know, if I use the voltmeter that can record more decimal points, my reading won't be 2.6, it will be more, something different. That means from 2.55 to 2.64, the reading by 1 decimal point is going to be 2.6. there is uncertainty. So if you are recording 2.6 volt, if you are getting 2.6 volt means you can't accept it as a 2.6 because you are not sure. You are not sure. The reading could be somewhere between 2.55 to 2.64. If it is 2.55, it will record 2.6. If it is 2.56 also, it will record 2.6. If it is 2.57 also, it will record 2.6. If it is 2.58, 2.6, it will record 2.59 also, 2.6, 2.60 also, 2.6, 2.61 also, 2.6. So like that, if you are getting 2.6 volt when you are using 1 decimal point voltmeter, you are not sure about the reading because it could be somewhere between 2.55 to 2.64. 2.55 to 2.64. So there is a possible range somewhere from 2.55 to 2.64 is the outcome. When I get 2.6, I can't accept it as 100% accurate as 2.6. So mathematically what we do, you can see that 2.55 to 2.64. So when we in physics sometimes if you want to show something in a mathematical model, we need a symmetrical thing. So what we say, there is uncertainty. When I get 2.6 volt, there is uncertainty which is 2.6 plus or minus 0.05 volt. That means 2.6 minus 0.05, that is 2.6 minus 0.05, we will get 2.55. 2.6 plus 0.05 we will get 2.65. Yeah, you might say this is 2.7. Yes, I know that, but up to 2.64 it's going to be 2.6. So mathematically when we put, we need a symmetrical pattern. So that's the reason we take the same value as plus or minus 0.05. You know the least count, the resolution of this one is 0.1. Half of 0.1 divided by 2 is 0.05. Half of this is 0.05. That is called the uncertainty. The reason I hope you understood, because if the reading is from 2.55 to 2.64, but here we take 2.65 so for mathematical model. So 2.55 to 2.65, it reads 2.6 when you are using 1 decimal point. That means we can show this uncertainty, the range. I am not sure when I am getting 2.6 volt means I am not sure how much is it. It could be somewhere between this. That range we obtain by using plus or minus half of this resolution, half of this one. That is called uncertainty. That's the reason we use the idea called uncertainty. I hope you understood the idea, the meaning of uncertainty. That's the reason your teachers would have told always uncertainty of a measurement is half of the resolution. Half of the resolution, you know resolution and least count are the same. So half of the resolution or half of the least count of the instrument is the uncertainty of a measurement. Uncertainty of particular one measurement. Remember, for a particular one measurement, uncertainty is half of the least count. Keep it in mind. So that's the reason I explained why we take this way. This is the reason. Same I can explain. Now here I told about digital meter, digital voltmeter. Same way for analog voltmeter also I can explain this, or analog voltmeter or maybe analog weighing scale. There also we can explain, I'll explain that now, how the uncertainty idea comes when we are using analog meters. This is digital meter I told, so these are digital meters. Analog meters also, there will be uncertainty, we take it as they are also half of the least count. So I hope you understood the meaning of half of the, why do we take uncertainty as half of the least count. This is the reason. Okay, it's true not only in physics, even chemistry, biology also, this is the same theory. So that is uncertainty of a measurement is half of the least count. Keep it in mind. Uncertainty of a measurement. Okay, so the same analog weighing scale. Okay, that weighing scale, imagine that weighing scale only integer divisions, that is 0, 1, 2, 3, 4, 5 kilograms, no subdivision, no other mark, so no other division. So this weighing scale is not showing 0.1 or 0.5 scale divisions, just only 1 kilogram, 2 kilogram, 3, 4, 5 kilograms are shown, right? Imagine a weighing scale, something like that. Okay, so you are keeping an object on the analog weighing scale on this one. So the pointer stays somewhere here. So when you see that, you are able to identify the pointer is slightly more than mid of 1 and 2. So mid of 1 and 2 is 1.5, we know that, but we don't have a division there. It's not marked. So I can't give a value 1.5 because it's not marked here. The divisions are only integers 1, 2, 3, 4, 5. Right? So when you keep an object, the pointer shows a point which is eye level. You can see that it's slightly more than mid of 1 and 2. So it's not 1.5, maybe 1.6 or 1.7, no, we don't know. But more than 1.5. So when you are writing a value, the reading of it, you can't say I can't give a value because the meter, there is no division. No, you can't say that. According to the given instrument, you have to give a reading. So the reading, you will say the mass is equal to little more than 1.5. I said more than the mid of 1 and 2. So you will say this as 2 kilogram. Now another object is kept on the same weighing scale. After removing the first object, you are keeping the second object. There, the meter reads, the pointer stays slightly less than mid of 2 and 3. Same meter, same weighing scale. Now, second object is kept after taking out the first object. You are going to measure the mass of the second object also. So there, when you keep it, the pointer is somewhere slightly less than mid of 2 and 3. Mid of 2 and 3 is 2.5, but I can't give 2.5 and 3 because there is no division like that, not marked. So it's slightly less than 2.5. Means here also you will say M2, the mass M2, this is mass F1. M2 also you have to give a value. You can't say I can't give a reading. According to the given instrument, you have to give a value. So you will say the closest value 2 kilogram. Understand? So here also, from the range that is from 1.5 kilogram, that is from the mid of 1 and 2, from 1.5, but I can't read as 1.5, but I am saying is 1.5 kilogram to 2.4 kilogram, slightly less than the mid of 2 and 3, that is 2.4 could be. You are going to write the reading as 2 kilogram. So these readings are going to be written as 2 kilogram. So I told that when we are showing it in mathematical model, mathematical format, we need a symmetrical. So 1.5 to 2.5 we can take it. So there you know 1.5 to 2.5. So this reading I can say, when I record 2 kilogram, here I can say the reading, the mass is somewhere between 2 plus or minus 0.5 kilogram. So if you are recording 2 kilogram, if you are writing, when you are writing 2 kilogram, you can say I don't know the actual mass of the object, but it could be somewhere between 1.5 to 2.5. 1.5 to 2.5, but I am not sure how much is it, but I have to write according to the given divisions or the scales on the weighing scale. I have to give the value. I can't put a value which is not marked on the scale. Either otherwise I have to calibrate it. Calibration is we don't do in your syllabus. So according to the given scale, I had to give a value. So I will give 2 kilogram, but actual mass could be somewhere from 1.5 to 2.5. It could be somewhere from 1.5 kilogram to 2.5 kilogram. So you know that 0.5 kilogram is half of 1 kilogram. So here the least count, the resolution of this weighing scale is 1 kilogram. Divided by 2 is 0.5 kilogram. That is taken as the uncertainty of this weighing scale. That's the reason we take uncertainty is always half of the least count, whether it's analog instrument or digital instrument. The uncertainty is always taken as half of the least count. This is true in physics, chemistry and biology also. Okay. Okay, so the next thing is percentage uncertainty. So percentage uncertainty means that is uncertainty divided by the measurement. Measurement means what you write as a measurement or reading into 100%. Okay, so that's not a big thing to explain, but remember that shortly we can write percentage sign U. That's normally the mark scheme also they accept. Percentage uncertainty is written as percentage sign with u. Percentage uncertainty is equal to uncertainty of the instrument or uncertainty of the measurement. That is half of the least count for a single measurement. For a measurement, half of the least count of the instrument. Uncertainty over, you can say measurement or reading, either one I can say. Into 100%. Into 100%. Normally, in your syllabus, we give this in two significant figures. That's the way the mark schemes, they expect you to give the final percentage answer in 2SF. Okay, that should be given in two significant figures. Okay, remember that, keep it in mind. Okay, so the calculations related to uncertainty is not finished. I had to continue. But before that, I had to introduce certain idea regarding error and uncertainty. Careful, uncertainty is not an error. Sometimes students have wrong idea. Uncertainty is also error. No, error is different. Error means it's a mistake. It happens due to some mistake. So the error, there are two different types of errors in experiments. We call, that is systematic error, then the other one is called random error. So this uncertainty is not an error, because uncertainty means, that means your instrument is unable to record more precisely than the given resolution of the instrument. Okay, so it's not an error. You are able to make record only that value. Say for example, I told that analog weighing scale. Yes, we know that the pointer is somewhere between 1 and 2, but little more than mid of 1 and 2, little more than 1.5. I know that, but I can't write 1.5. So I wrote it 2 because it's more closer to 2 than 1, right? So that is not an error. That's the only reading I can record by using the given instrument. It's not an error. But error means some mistake. It's like a mistakes that we can make during experiment. Not purposely making mistakes. Sometimes we make mistakes. That means that is error. There are two different type of errors. First is called systematic error. The other one is called random error. Right. What is systematic error? What is random error? Okay, what is systematic error? Systematic error means the error due to a default or mistake in the instrument, or the error due to misuse of an instrument by the experimenter. For example, you know, you would have learned that in school. You would have checked for zero error when you are using micrometer screw gauge. That means when you close the micrometer screw gauge and when the two jaws touch each other, the zero mark of the line on the cylinder and the zero mark of the scale, the main scale, they should coincide with each other. Otherwise, there is zero error. All the readings are going to be increase or decrease due to the initial error or zero error in the meter. Or maybe when you are thinking about voltmeter, imagine analog voltmeter. So when you are using analog meter, not only voltmeter, analog meter, this is a zero mark. Maybe this is again say something like 0.5, 1, 1.5, 2, 2.5. These are the divisions marked on the analog voltmeter. But initially, when you are not applying any voltage before you connect the voltmeter to any circuit, the pointer is somewhere here. The pointer is somewhere here. Imagine the pointer is at here. Okay, the pointer is staying here at 0.5, even when you are not applying a voltage. So what's going to happen? Actual voltage, if it is 1.5, it's going to read 2 volt, because already it's giving a value that is called zero error. Okay, same way micrometer screw gauge also, there will be zero error, but that's called zero error correction we should do. Here we can do error correction. There's a small screw in the analog meter. By turning that small screw, you can bring the pointer to 0, right? But if you can't bring it, you had to get a new instrument. Better to get a new instrument. This instrument should be replaced with a proper instrument. Even micrometer screw gauge, there's a method called zero error correction, not in your syllabus. If you want, you can do zero error correction, right? Or you have to replace the micrometer screw gauge by a new micrometer screw gauge that does not have any zero error. So this is called systematic error. Systematic error means an error due to a default or error due to a fault in the instrument is called systematic error. There's one more systematic error that is due to misuse of instrument. You know, if you give just a meter rule to an ordinary person, he knows how to measure the length. But if you give a micrometer screw gauge to a person who does not know how to use the micrometer screw gauge, he might record completely wrong reading. So when you are in unit 1 paper, sometimes, or unit 3 paper also, sometimes they give a photograph of a micrometer screw gauge and ask the students to write the reading. So they are all students, most of the students write the correct answer, but there are students, they might make mistake because they are not sure how to take the reading by using a micrometer screw gauge, right? So using micrometer screw gauge is not like using a meter rule. You should know how to take a reading by using micrometer screw gauge. So if you don't know, you might record the value in a wrong way. That is also systematic error. Okay, so these are the errors. These are errors actually. Okay, these are called systematic errors. Okay, random error. What is random error? Normally we can say random error means inability of the instrument to record the same value when the same measurement is repeated. Okay, what do you mean by that? Say for example, you are dropping a ball, right? You are dropping a ball from a particular height, maybe 1 meter, right? You know that you are keeping the ball exactly at 1 meter height. So from 1 meter, you are dropping a ball. At the aim of the experiment, what's the time taken by the ball to reach the ground? Okay, that's the experiment. You are going to use a stopwatch. So you are holding the stopwatch and you are holding a ball and you are just releasing, you are making a proper setup to release the ball. And when the ball is released, you should switch on the stopwatch. When the ball hits the ground, you should switch off the stopwatch. That's the aim of the experiment. There, when you repeat the experiment, you won't get the same timing always. The timing will differ. You know the reason, that is due to reaction time. That is called random error. When the repeated measurement, so you are always dropping the ball from the same height 1 meter, you are using the same stopwatch, you are repeating the experiment again and again. So there, when you do the experiment, you are getting different values, right? So that type of measurement is called random error. But this random error also could become a systematic error. How is it possible? Little too much. There are no such questions, but I'll tell you, there's a thing you better know that random error also could become a systematic error. For example, say we can calculate that theoretically what could be the time taken. Imagine the drag forces are negligible. Okay, we can calculate the time taken by using S equal ut plus half at squared. Imagine this height little more. Imagine the height is 8 meter. Easy to get a big value for time. S equal ut plus half at squared. If you are using S is 8, you are dropping from rest. You see plus half 9.81 t squared. Find the t. So when you find the t, you will say the theoretical value of time taken. So that will be 1.28 seconds. That's the theoretical time. We assume the drag force is negligible and there is no drag force. So this is the time taken by the ball to fall through a height of 8 meters, and the friend is measuring that time. Okay, so when he repeats this experiment 4 times, he might get the times, the repeated measurements maybe, he might get 1.26 seconds, 1.26 seconds, then 1.24 seconds, 1.27 seconds, sorry, 1.27 seconds or 1.29 seconds. Then repeated measurements seconds, 1.29 seconds, this also one I made mistake, 1.24, 1.26, this is less than that one, this is also less than that, this is more than that, then 1.31 seconds, 5 readings, 1.28 seconds. actual reading also is getting at once. So here you can see that when he repeats 5 times, this reading is less than that, this is less than that, this is more than that, this is more than that, this is equal. Like that he is getting 5 readings. So when you find the average of this one, when you find the average of this 5 readings, because we don't know which one is the correct, because you are not getting the same value when you repeat it. So when you find the average of it, it could become closer to 1.28 seconds. So that's the reason we take that. So when you find the average time, so average time of these 5 readings becomes 1.276. If the clock can read only 2 decimal points, we have to give the average also in 2 decimal points. So 1.276 is becoming 1.28 seconds. So it's becoming almost accurate. So accidentally it came for these values, but that's the reason normally even in IGCSE you say repeat the measurement and find the average. Why? To reduce the random error. Reduce the random error. This is the reason we repeat and find the average. But it could become a systematic error. The repeated readings and finding average, sometimes it won't work. Say for example, imagine you are dropping the same experiment, you are dropping the ball and you are taking 5 different readings. The repeated measurements are something like 1.24 seconds, 1.26 seconds, 1.22 seconds, 1.27 seconds and 1.26 seconds. All readings are lower than this one. All the readings, what I wrote here, 1.24, 1.26, 1.22, 1.27, 1.26, they all are lower than this. Here, by taking the average, you won't bring it to closer to it, because this is going to be a systematic error. That means always, so the reason for this values, like once it becoming lower than that, lower than actual value, higher than actual value, higher than actual value, equal to value, actual value means it's like you are dropping the ball, you are switching on the stopwatch and you are, when it hits you are switching off. So there you might release the ball before switching on, or you might release the ball after you switch on. Slight difference can happen. That's called random error due to the reaction time problems. But here you are making the same mistake again and again, something like a zero error. But I told in always the reading is greater than, less than the actual value. So this repeated measurements won't give you a random error. That is going to be a systematic, because the error is always on one side, lower than the actual value. The average, by finding the average, could become closer to the actual value when the repeated measurements are, few of them are more than actual, few of them are less than actual, less than more. So when you find the average, they can get closer to the actual. But here they all are lower than actual value. This is going to be a systematic error. Anyway, but you don't need too much about this type of errors. Normally we say same as what we tell IGCSE students. Repeated measurements, make or find the repeated measurement and find the average of these repeated readings to reduce the random error. So random error could be reduced. Random error could be reduced by taking repeated measurements and finding the mean or average value of it. Systematic error you can't reduce by taking repeated measurements. Systematic error I already explained, that zero error. No point of taking zero error repeated measurements. You won't get, because always the reading will be lower than actual value or greater than actual value if there is a zero error of a micrometer screw gauge. Okay, that's what I told. Always the error is on one side, lower than actual value. Same way, you might repeat an experiment where all the readings could be more than actual value. There also, no point of taking average. You won't get the average value closer to the actual value. Okay, so anyway, but random error means we generally say repeated measurements could reduce the random error. So take repeated measurements and find the mean value, that will reduce the random error. Systematic error, that you can't reduce it. So only to avoid systematic error, something like zero error, you have to replace the instrument with the correct instrument which does not have any zero error. Okay, so next, what's the use of this percentage uncertainties? Percentage uncertainty is used to compare two different, the same measurement by using two different instruments. Normally, if the percentage uncertainty is smaller, we say that particular measurement is more accurate or more precise. Okay, if the percentage uncertainty is smaller, we say that measurement is more precise and that is the most accurate measurement. Say for example, diameter of a coin could be measured by using vernier caliper. Also, it could be measured by using a set square and meter rule. Is it? If you are measuring the vernier by using vernier caliper, I am drawing only the two jaws of the vernier caliper. The coin should be kept between the two jaws like this. Is it? I am not conveying that. These are the two jaws, the vernier caliper. You can measure the diameter of the coin. Or if you are using the meter rule, if you don't have vernier caliper, you can measure the diameter. You have to keep the coin like this on a white sheet. Keep two set squares like this. These are the techniques you should know to keep two set squares like this. And on the white sheet, mark the 2 points of the edge of the two set squares and measure this length by using a meter rule. You can measure the reading by using a meter rule. That way also you can measure the diameter of a coin. Okay, so when the diameter is measured by using vernier caliper, the diameter is recorded as 15.8 millimeter. Here, the diameter is recorded when using meter rule 16 millimeter. Only 0.2 millimeter difference. Which reading is more accurate if they ask? We have to use the percentage uncertainty. So when the vernier caliper is used, percentage uncertainty is given by uncertainty of the vernier caliper. We know half of the least count. I already explained least count or resolution of a vernier caliper is 0.1 millimeter. Half of it is 0.05 millimeter divided by the measurement, that is 15.8 millimeter into 100%. So that should be given in two significant figures. You will get 0.32%. Here, when you are using a meter rule, the percentage uncertainty, you know, meter rule uncertainty is 0.5 millimeter. Resolution or the least count is 1 millimeter. So 0.5 millimeter divided by 16 millimeter into 100. So here you will get 3.1%. So this percentage much smaller than this one. That means the measurement by using vernier caliper is more precise or more accurate because the percentage uncertainty is smaller means more accurate. Okay, so like that when we compare two readings, we need the percentage uncertainty. Okay, so this technique also you should better know that larger the measurement, lower the percentage uncertainty and hence lower the uncertainty for a particular quantity. For example, I'll take an example. Imagine an example is a student wants to measure the thickness of a sheet. So when he measured thickness of a sheet, maybe paper or cardboard, whatever it is, when he measured the thickness of a sheet by using micrometer screw gauge, the thickness measurement becomes 0.44 millimeter. So thickness of a sheet is 0.44 millimeter. He measured by using micrometer screw gauge. Okay, what could be the uncertainty of this measurement? You know you are using micrometer screw gauge. So the uncertainty of the measurement is half of the least count of the micrometer screw gauge. Least count of the micrometer screw gauge is 0.01 millimeter. So the uncertainty will be 0.005 millimeter. Is it? So the percentage uncertainty of thickness of one sheet, percentage uncertainty in thickness of a sheet paper, uncertainty in the measurement of thickness of a sheet, he measured by using micrometer screw gauge. Least count is 0.01, half of it 0.005 millimeter over the measurement 0.44 millimeter into 100%. So that's going to be 1.1%. We normally give in 2 SF, so 1.1%. Okay. Now, another student, what is he doing? He is measuring the same thickness by keeping 50 sheets together, and he is measuring the total thickness by using the same micrometer screw gauge. Okay, so when he keeps 50 50 sheets, identical sheets together, the total measurement becomes 20. That's one sheet is 0.44 millimeters. So when he takes 50 sheets, okay, thickness of 50 sheets, so that is actually, he is using the same micrometer screw gauge. We know that 50 into 0.44, that becomes 22 millimeter. Okay, 22 millimeter. So he is taking larger measurement. So he is going to divide this by 50. You will get the same answer. When he measured the thickness of 50 sheets, he is getting 22 millimeter means when to find the thickness of one sheet, he will divide this measurement by 50 because there are 50 sheets. He will get the same answer, 0.44 millimeter. But which measurement is more precise? That's a purpose of this analysis, right? I told that lower the percentage uncertainty or lower the uncertainty, that is the most precise way of measurement, right? So he's getting 22 millimeter. Okay, so here the percentage uncertainty for thickness of 50 sheets equal, that is, he's using the micrometer screw gauge, so 0.005 millimeter divided by 22 millimeter into 100%. So there he will get the percentage answer will become 0.02 percentage. 0.02 percentage. Much lower than this percentage. Okay. Now to get the thickness of one sheet, we are going to divide the measurement, which is 22 millimeter, by 50. When you are dividing or multiplying a measurement, the percentage uncertainty will remain the same. Keep it in mind. When you are dividing or multiplying a measurement by using a number, you are dividing or multiplying a measurement by a number, there's no change in the percentage uncertainty. The percentage uncertainty will remain the same. So, percentage uncertainty of one sheet here going to be 0.01 percentage. So, he will say percentage uncertainty in thickness of one sheet that will be same as 0.02 percentage. Remember that, whenever a measurement is multiplied or divided by a number, the percentage uncertainty of the measurement will remain the same. So that's going to be 0.02 percentage. Already that is smaller than 1.1 percentage. Now, what is the uncertainty in the measurement of one sheet when he is measuring 50 sheets and divided by 50? So here, you know that uncertainty, he is measuring one sheet. So when he measures the thickness of a sheet, 0.4 millimeter means when he include the uncertainty plus or minus, here he has to write this one must be written as 0.44 millimeter plus or minus 0.005 millimeter. So the range you can find it in this one, but I don't want to find the range. But this is the thickness of one sheet, the range of one sheet, 0.44 millimeter minus 0.005 to 0.44 millimeter plus 0.005 millimeter. That will be the range of the thickness of one sheet when he is measuring thickness of just one sheet by using micrometer screw gauge. He is using the same micrometer screw gauge, but here he is measuring 50 sheets. Because of measuring 50 sheets, the percentage uncertainty has dropped. Now, if you want to find uncertainty in thickness of one sheet, we know thickness of one sheet is, we know that 0.44 millimeter, because 50 sheets is 22 millimeter, divided by 50, you will get 0.44. So 0.44 millimeter, that's the thickness of one sheet. But percentage uncertainty now, because he measured 50 sheets, percentage uncertainty is 0.02 divided by 0.02 percentage divided by 100. Find the percentage. Normally what we do the values, is it? So here you will get, that's going to be very small, 0.000, one more 0.88 millimeters. See how much it is dropping now. In this one, here the range is 0.044 plus or minus 0.005. That's a range, I can find it if you want. This range will be, I think, 0.435 to 0.435 to 0.445. That's the range. 0.435 to 0.445 is the range. Now here, the range is going to be, now in this one, the range is going to be 0.44 millimeter, same as this one, but plus or minus very small value, 0.00088 millimeters. So you know that very small value means range is going to be very small. The range, here the range, if it is from here to here, the values, this is 0.435 millimeter, this is 0.445 millimeter. This range is going to be very small. If you want, you can calculate. The range is very small. Smaller the range, more precise reading. Smaller the range, more accurate. Smaller the uncertainty, more accurate. So the advantage here, how we got this smaller uncertainty? By taking a larger measurement. We took the measurement of 50 sheets. This student took the measurement, the thickness of 50 sheets. Because of that, his uncertainty becomes very small. But percentage uncertainty will remain the same. This percentage uncertainty, when you are dividing a value, the percentage uncertainty won't change. Here the 50 sheets, the percentage uncertainty is 0.02. Thickness of one sheet also, the percentage uncertainty same, 0.02. But you can compare this percentage uncertainty, this percentage uncertainty. This is, we are taking larger measurement, smaller percentage uncertainty, smaller measurement, larger percentage uncertainty. So the advantage here, when you are taking larger measurements, the same quantity, we are going to take a larger measurement and going to divide by a certain number. Here the number is 50. You can reduce the percentage uncertainty. By reducing the percentage uncertainty compared to this percentage uncertainty, you are reducing the percentage uncertainty, you can reduce the uncertainty also. So if we can take larger measurements, it's better to take the large measurements by using the same instrument, because we can reduce the percentage uncertainty and hence we can reduce the uncertainty in the quantity that we are going to calculate. But again, when you are dividing or multiplying a particular measurement by a number, percentage uncertainty will remain the same. Percentage uncertainty will remain the same. But uncertainty is dropping here. Here we made an approximation everywhere. Here it's not accurately 0.02, there is 0.024, something like that coming. Here if I approximate this to 0 point, then it will become 0.0001 millimeter. We can write this like that. If we approximate, if we make it 0.0001 meter, 0. Yeah, that could be approximated to 0.0001 millimeter. It's okay, it doesn't matter. 0.00088 millimeter or 0.0001 millimeter. Same if you want to put it. Okay, so this is another example. How the larger measurements gives lower uncertainty and percentage uncertainty. In diffraction grating, unit 2, diffraction grating, there's a laser torch. This is the zeroth order, n equals 0, first order, second order. So you know that the angle of diffraction theta we measure by using tan theta, is it? We should know the distance of the screen from the diffraction grating that I just took 1 meter, and the distance of the first order from the 0th order measured by using meter rule 18 centimeter. On the other side also, distance of the first order from the 0th order it's 18 centimeter because it's symmetrical about the 0th order. The bright bands are formed symmetrically on the screen. So if it is at 18 centimeter from 0th order, this also will be 18 centimeter from the 0th order. Okay, so here also our aim is finding the theta. How to find the uncertain theta, the trigonometric functions, I'll tell you later. I'm not going to tell that now, I'll tell that later when I start how to find the uncertainties in trigonometric functions, because you had in unit 2 n equals sin I over sin r, refractive index. So you should know how to find the uncertainty in the trigonometric functions like sin theta or cos theta or tan theta, but tan theta we don't use, only the sin theta we use. So here how to find that uncertainty in theta I'll tell you later, but here we are measuring the distance of the first order from 0th order. This is 1 meter, so we use tan theta to find the theta. But how the uncertainty in this measurement is going to affect when we measure the total distance from first order to first order and divide by 2. The measurement has no difference. So from 0th order to first order 18 centimeter, from first order to first order 36 centimeter, 18 plus 18 centimeter, 36 divided by 2, that also 18. So there is no change in the measurement. But the advantage here, when we take the measurement from n equal 1 to n equal 1, that is larger measurement, and divide by 2, we can reduce the both uncertainty and percentage uncertainty. I'll show you that now here. Now okay, a student is measuring from 0th order to first order, just he is measuring 18 centimeter, first student, right? So the first student is measuring, the aim is measuring the distance of first order from 0th order. So he is measuring by using meter rule from n equals 0 to n equal 1. He measured it as 18 centimeter. You are using meter rule. Least count is 1 millimeter. So the uncertainty of the measurement is 0.5 millimeter. So there the percentage uncertainty is going to be, uncertainty is 0.5 millimeter divided by 18 centimeter means 180 millimeter into 100%. So it's going to be anyway, that's going to be 0.32 percentage, sorry, 0.28 percentage. So his measurement, the distance, from here to here I'll put the distance he is going to measure 18 centimeter plus or minus 0.5 millimeter. So 0.5 millimeter is the uncertainty of the measurement. If you convert to centimeter, it's going to be 0.05 centimeter. So you can find the range 18 minus 0.05 to 18 plus 0.05 is going to be the range of that measurement. Okay, the second student, what is he doing? He is measuring the distance from first order to first order as 36%. So there the percentage uncertainty is going to be, he is using the ruler. So the percentage uncertainty is going to be the same as 0.5 millimeter. He has larger measurement, 36 millimeter means 360 millimeter, 36 centimeter means 360 millimeter into 100%. So he will get percentage uncertainty. You know this is becoming double means anyway it's going to be 0.14%. Right. Now what is the uncertainty in his measurement? So now he is going to divide this 36 centimeter by 2, he is going to get 18. Now he is going to get the uncertainty so percentage uncertainty for his measurement of 36 is 0.14. So he is going to divide this 36 by 2. I told when you are dividing or multiplying a measurement, percentage uncertainty will remain the same. So the percentage uncertainty will be 0.14. So now he is going to calculate 18 centimeter into 0.14 percentage over 100. So that is the uncertainty for this student who measured from n equal 1 to n equal 1. Now we will get the uncertainty will be for him, it's going to be 0.025 centimeter. So now this student will say the distance between n equally 0 to n equal 1, that is 18 centimeter plus or minus 0.025 centimeter. Now look at here. This range is smaller than this range. Smaller the range, more precise because uncertainty is less. Okay, so the same value they are getting, but the uncertainty becomes smaller when he takes larger measurement. Okay, so this is a good example to show larger the measurement, lower the percentage uncertainty, lower the percentage uncertainty, and hence lower the uncertainty. But when you are dividing the measurement, which is 360 millimeter, is 36 centimeter, by 2 to get this value, the percentage uncertainty will remain the same. Percentage uncertainty will not be divided. Okay. Okay, so I'm going to introduce another technique. Now I already told that when a measurement here, now forget about the first one, second one, measurement is 360 millimeter, that is 36 centimeter. When that measurement is divided by 2, this measurement is divided by 2, you will get this length. That is the aim of this experiment. So when that measurement is divided by a number, the percentage uncertainty remains the same. Here 0.14, here also 0.14. So when a measurement is divided or multiplied by a number, the percentage uncertainty will remain the same. That you must know. But when the measurement is divided or multiplied by a number, what will happen to the uncertainty? Carefully look at here. The uncertainty of this one is 0.5 millimeter. When I am measuring 36 centimeter, 350 millimeter means 36 centimeter. The uncertainty is 0.5 millimeter. So I am dividing this 36 centimeter, which is 360 millimeter means 36 centimeter, by 2 to get this distance, which is 18 centimeter. So when I divide it by 2, now see the uncertainty 0.025, this is 0.5. When you divide this uncertainty 0.5 by 2, you will get this one. Okay, so keep it in mind, when a measurement is divided or multiplied by a number, the number could be anything, it could be even pi, you know pi, 22 by 7, okay, you can get it in the calculator. So when a measurement is multiplied by or divided by a number, percentage uncertainty will remain unchanged, percentage uncertainty will remain the same, but uncertainty of the measurement will be divided or multiplied by the same number. When the measurement, which is 36 centimeter, is divided by 2 to get 18 centimeter, the uncertainty 0.5 becomes 0.025, means uncertainty 0.5 is also divided by 2, which becomes 0.025. So when a measurement is multiplied by or divided by a number, uncertainty also will be divided or multiplied by the same number. If you are say for example, you are measuring a diameter of a coin. I'm going to give that as a second example. Now I'm going to give that as a worked example. When your aim is measuring the circumference of a coin. Normally we don't have any instrument to measure the circumference. Otherwise we had to use a string and put it around the circumference and measure it. Okay, but normally what we do, we measure the diameter of the coin, or like a coin, by using vernier caliper, and we calculate the circumference by using pi d or 2 pi r. 2 pi r or pi d is the circumference, is it? Circumference is equal to 2 pi r, some books they say 2r is equal to d, so that is we can say pi d. So if the diameter is measured by using a vernier caliper, the uncertainty of the vernier caliper is 0.05 millimeter, half of 0.1 millimeter is the uncertainty of the measurement of diameter. So what is the uncertainty in C? Uncertainty in C, I'll do it as again after erasing the board, but I'm just showing it. Uncertainty in C means this is the diameter. Diameter is multiplied by pi to find the C. So uncertainty in C is equal to pi into uncertainty in D, 0.05 millimeter. Okay, so when a measurement is divided or multiplied by a number, uncertainty also will be divided or multiplied by the same number. So first one can ask, what is the uncertainty? We can't measure the radius by using vernier caliper. We can measure the diameter. I showed it already. Keep the coin between the two jaws. So we measure the diameter. What's the radius? Yes, divide by this 2. 0.025 is the radius. What's uncertainty in what is the uncertainty in the radius means? The uncertainty of the diameter should be divided by 2. to find the uncertainty in the radius, uncertainty in the measurement of diameter, that is 0.05 millimeter, should be divided by 2. So when a measurement is multiplied or divided by a number, uncertainty also will be multiplied or divided by the same number, but percentage uncertainty will remain the same when you are multiplying or dividing a measurement by a number, no change in the percentage uncertainty. I think it's enough to say the same thing again and again. Okay, so I told that when a measured quantity is multiplied or divided by a number, its uncertainty also will be multiplied or divided by the same number. So we'll do an example based on that. Right, so in that example, we'll say that a student wants to measure the circumference of a circular disc. Okay, so the diameter of the disc is measured by using a meter rule, and he recorded it as 18 millimeter and measured by a meter rule. Okay, so uncertainty in this measurement is, you know that meter rule, uncertainty is 0.5 millimeter. So what could be the circumference? So the circumference of the circular disc, this is the diameter, 18 millimeter. The circumference is given by pi d or 2 pi r or pi d. So pi d we'll put it, pi d. So that's going to be pi, you know, you can get from the calculator, d is 18 millimeter. So it's going to be, the circumference will be 56.54 millimeter. You can give it in 3SF or 4SF. You can give it in 3SF, no problem, 56.5 millimeter, but I put it in 4SF. So that is the circumference. Okay, so we know the uncertainty in the measurement of diameter is done by use 0.5 millimeter because it's measured by using meter rule. So uncertainty in C, in circumference is equal to pi times uncertainty in D. So that is uncertainty in measurement of D. So that is pi into diameter is measured by using meter rule, which has uncertainty 0.5 millimeter. So solve it. That will be, you will get 1.57 millimeter. Okay, so we can find the percentage uncertainty. So if you want, you can find the range of the circumference, 56.54 millimeter plus or minus 1.57 millimeter is going to be the circumference of the range of the circumference. So range of the circumference is equal 56.54 millimeter plus or minus 1.57 millimeter. If you want to find the percentage uncertainty in the measurement of circumference, so the percentage uncertainty in the measurement of circumference, you can find it in two different ways. The first thing, simply the uncertainty in C, that is 1.57 over value of C into 100. That way you can do it. So that is fourth part. Percentage uncertainty in C equal uncertainty in C is 1.57 over the value of C, which is 56.54 into 100%. So normally we give it in 2SF, you will get 2.8%. Or you can do this way also. I told that a measured quantity, circumference is calculated. We will measure the circumference, calculated quantity, but measured quantity is diameter, that is 18 millimeter. Measured quantity is 18 millimeter. When you multiply that by pi, you got the circumference. Okay, so earlier I told when we are measuring the thickness of 50 sheets, there I told that. Now the percentage uncertainty of D is same as the percentage uncertainty. See, I told that when you multiplied or divide a measurement by a number, no change in percentage uncertainty. So that means you are multiplying the measurement D by pi and you are getting C. So if you find the percentage uncertainty of D, that will be same as the percentage uncertainty of C. So or we can do this one, yeah, by using that principle, percentage uncertainty in C is calculated by using pi d. So whatever the percentage uncertainty in D, same as the percentage uncertainty in C, because I told that when a measurement is multiplied or divided by a number, percentage uncertainty won't change. So the uncertainty in D, so I'm going to find the percentage uncertainty in D. Percentage uncertainty in C is equal to percentage uncertainty in D. Percentage uncertainty in D, you measure by using meter rule, which has uncertainty 0.5 millimeter, divided by the measurement of D is 18 millimeter into 100%. You will get exactly the same answer, right? You will get the same answer. So I told that when you multiply or divide a measurement by a number, percentage uncertainty will remain the same. But uncertainty will decrease if you divide the measurement by a number. By the same amount, it will decrease. If you multiply a measurement by a number, uncertainty also will increase by the same number. And we are told the same thing again and again. Okay, so the next thing is about adding or subtracting two measurements. Sometimes we won't be able to measure a particular physical quantity. We need to measure two different physical quantities, and by adding them or by subtracting one measured quantity from another measured quantity, we need to get the required physical quantity. For example, there is no instrument that can measure the change in temperature. Say for example, you are heating water in a beaker, initial temperature 28 degrees Celsius. You are measuring the temperature by using a liquid in glass thermometer or mercury thermometer. Normally the mercury thermometers, they have the least count is normally it could be 0.1 centimeter, 0.1 degrees Celsius thermometers are there, 0.5 degrees Celsius thermometers are there. We say the least count or resolution of the liquid in glass thermometer, that is the thermometer with mercury, its least count or the precision, the resolution, not precision, the resolution is 0.1 degrees Celsius. So you are measuring the initial temperature, then you are measuring the final temperature. Your aim, you need to find the change in temperature. For example, change in temperature, we need, you might remember we learned that in IGCSE when we are calculating the specific heat capacity or amount of heat absorbed by a element equal mc delta theta, or Q is equal to mc delta theta. The same thing is in unit 5 in Edexcel year 13 unit 5, but IGCSE also you came across this type of question. So Q or capital E we can put for the thermal energy absorbed or released by an object of mass m. This is the specific capacity. Delta theta or delta T, either one we can use, is the change in temperature. So change in temperature, directly we can't measure it. We need to measure the initial temperature. Initial temperature T1, that is for example we will say that is 31.2 degrees Celsius, measured by using a thermometer, maybe liquid in glass thermometer or thermocouple, whatever it is, right? The final temperature is 76.8 degrees Celsius. Okay, so the resolution of this measurement is uncertainty, or the resolution of this measurement is 0.1 degrees Celsius, because the reading is given in 1 decimal point. So the least count or the resolution is 0.1 degrees Celsius. So the uncertainty in measurement, of temperature generally is 0.1 0.1 1 divided by 2, so it's going to be 0.05 degrees Celsius. Okay, so here there's uncertainty 0.05, here also 0.05. So the change in temperature or increase in temperature delta T is equal to 76.8 degrees Celsius minus 31.2. So there is no instrument that can measure this one directly. You need to measure two different temperatures and you have to subtract. Okay, so you will get this change in temperature 45.6 degrees Celsius. Okay. What is the uncertainty in delta T? Okay. Whenever two measurements are subtracted, you need to add the uncertainty of the measurement. So the uncertainty of the measurement 31.2 degrees Celsius is 0.05 degrees Celsius. Uncertainty in the final temperature also 0.05. So uncertainty in delta T, you need to add the uncertainty of these two temperatures. Whenever two measurements are subtracted from the other one, uncertainties will be added. Remember that when two measurements are subtracted from, if one measurement is subtracted from the other one, then the uncertainties will be added. Not subtracted, added. Uncertainties will be added. Remember that. So uncertainty in delta T uncertainty in T1 plus in T2. So uncertainty in T1 is plus or minus 0.05 degrees Celsius. Here plus or minus 0.05 degrees Celsius, half of 0.1, 1 decimal point. So half of 0.1 is 0.05. So that will be 0.05 plus 0.05. That's going to be 0.1 degrees Celsius. Okay, that's the uncertainty in delta T. If you want to find the percentage uncertainty in delta T, uncertainty in delta T 0.1 degrees Celsius divided by delta T, that is 45.6 into 100%. So that normally give it in 2SF. If you solve it, you will get the percentage uncertainty in delta T. Same way, when you are adding two quantities also, uncertainties will be added. Whenever you add two measurements or three measurements can be added or four measurements can be added due to some reason. Whenever you are adding two or three or four, whatever the number of measurements, uncertainty of each measurement will be added. So remember that when measurements are added, uncertainty will be added. Even when the measurements are subtracted, a particular measurement is subtracted from the another measurement, there are also uncertainties of the measurements will be added. Remember that. Okay, so next thing is measuring the angle of a ram. That technique you should know. Okay, so that means we are doing a practical where you are measuring the acceleration of a trolley on a ram. You need to measure the angle. So there, how do you measure the angle of a ram with horizontal line? Say this is the horizontal line, this is the ram. You have 1 meter length of slope or 1 meter length of ram. You need to measure the angle theta. You can vary the angle theta. Which instrument will you use to measure this angle? Okay, so here which instrument is suitable to measure the angle means normally we don't use protractor because the resolution or the least count of a protractor is 1 degree Celsius. That the smallest angle that could be measured by using a protractor is 1 degree Celsius. But if you are using a trigonometry, here by using tan theta or sin theta, what could be the smallest angle that we can measure means, yes, we can measure the this height. This height could be kept at 1 millimeter. We can keep a ruler. You can keep a ruler. To ensure the ruler is in vertical, you can use a set square. So the smallest angle that could be measured is 1 millimeter. By using a meter rule, the smallest angle that could be measured is 1 millimeter. So this is 1 millimeter, this is 1 meter. So what could be the smallest angle theta we can measure? If it is like a protractor, the smallest angle that could be measured is 1 degree Celsius. You can see the protractor, the smallest division shown is 1 degree Celsius. But if you are using this method, tan theta, trigonometry calculated, tan theta equal opposite 1 millimeter over 1 meter means 1000 millimeter. What could be the smallest angle? Sorry, not tan theta, sin theta. Sin theta, opposite value. Sin theta, 1 millimeter over 1000 millimeter. What could be the smallest angle that could be measured? If you calculate, you will get 0.057 degrees. So this is the smallest angle we can measure by using this method, by using a ruler. Measure this height, that is 1 millimeter. Measure this height, is already I told 1 meter. So the smallest angle that you can get it is 0.057 degree, much smaller than the resolution or the least count of a protractor. So this is the better method to measure the angle of a ramp. Okay, so how to find the uncertainty in measurement of angle theta? As I explained earlier, you are measuring the angle of a slope by using a meter rule. Okay, so here I am not earlier I explained what could be the minimum angle that could be measured. Now a particular measurement, say for example slope is kept, the length of it is 21 centimeter, and a student wants to measure the angle theta. When it makes an angle this theta, it's at an angle, the height is, you know how to measure by using ruler. Keep a ruler with a set square, I already showed it. This height is 4 centimeter, right? So 4 centimeter. A student wants to measure the angle theta, so sin theta is equal to opposite 4 over 21. You will get theta, that will be equal to 11 degree. Okay, that problem. Okay, now we know how to measure the angle theta. Now what is the uncertainty in this angle theta? Okay, so I used sin theta. Sin theta, this is 4 centimeter, this is 21 centimeter, that is 4 centimeter divided by 21 centimeter. Both 4 centimeter and 21 centimeter are measured. 4 centimeter and 21 centimeter are measured by using a meter rule. Using a meter rule. Okay, so its uncertainty is 0.5 millimeter. We know that the least count is 1 millimeter, uncertainty is 0.5 millimeter. So this 4 centimeter, so the height is equal to 4 centimeter. We have to give it in the millimeter because uncertainty is in millimeter. So that is going to be 40 millimeter plus or minus 0.5 millimeter. This length, I'll call this as distance d, or length, whatever it is. Distance d is equal to 21 centimeters. So 21 means 210 millimeter plus or minus 0.5 millimeter. We got sin theta by using sin theta is equal to d over h. You'll write the full thing. That is, this is h, this height is h. That is sin theta equal h over d. That is 4 centimeter over 21 centimeter, and theta becomes 11 degree. Right, okay. So h and d are the measured quantities by using meter rule. They have uncertainty. So because of the uncertainty 0.5, 0.5, because of these uncertainties, there will be uncertainty in theta also. That is the question, how to find the uncertainty in theta. Okay, so remember the method. Rarely comes, this is mainly comes in A2 unit 6 paper, but better know this method because same thing where we use protractor. I'll tell you how to find the uncertainty in refractive index, n equals sin I over sin r, where I and r normally when we do practical, I and r we normally measure using protractor. So the same idea there also. I'll tell you how to find it next I'm going to explain that one. Okay, so here how to find the uncertainty in theta. So there we find what could be the possibly maximum angle theta. So that is sine theta, what could be the maximum angle due to these uncertainties. So to get the maximum value, h must become maximum, that is the numerator, the denominator should become the minimum quantity. Then sine theta will have a bigger fraction that will give maximum value of theta, is it? So sine theta maximum is equal to, the numerator should become maximum due to this uncertainty, that is h is 40 millimeter plus 0.5 millimeter over, the denominator should become d, that's a denominator, that should become the lowest value to make this fraction maximum to get the theta maximum. So that is going to be the minimum, that is 210 millimeter minus 0.5 millimeter. Okay, so solve it, this one. So that's going to be 40.5 millimeter over 210 minus 0.5, 209.5 millimeter. Find the theta maximum, you will get 11.1 degree. So that could be the maximum angle in the uncertainty due to the maximums. I am going to find the uncertainty, so that could be the maximum value of theta due to the uncertainties in the measurement of h and d. Okay, so we will find the sine theta minimum also. Sine theta minimum means we should make the numerator minimum, denominator maximum. So it's going to be 40 millimeter minus 0.5 millimeter divided by 210 millimeter plus 0.5 millimeter. So from this theta minimum, you can solve it by using calculator. Theta minimum will become 10.8 degree. Okay, so we have two different values, the extreme values for theta max and theta minimum, but actual theta is 11. Okay, so uncertainty in theta. How to find the uncertainty in theta? Remember the method. You would have done repeated measurements. I haven't done it. Same way, repeated measurement, we take half max minus min. The same way here also. I haven't done that repeated measurement. I'm going to tell that, but I finish these single measurements and go to the repeated measurements. So uncertainty in theta is equal to half theta max minus theta min. So half into theta max is 11.1, 10.8. Give it with the same decimal point. So you will get that is going to be 2 decimal, you can give 0.15 degree. That's the uncertainty in theta. If you want to find the percentage uncertainty in theta, uncertainty in theta 0.15 over value of theta we found in 11 degree into 100. So that will be percentage uncertainty in theta, that will be 1.4 percentage. Okay. So this is the method. We find theta max, theta min by using, when we are measuring the angle, by using trigonometry, sine theta, where the height and the length are measured by using meter. So there we need to find the two values of theta. Then we do like this and get the uncertainty in theta. Okay, next thing about finding the uncertainty measurement of refractive index, single measurement, sin I over sin R, not with graph, just single measurement. You measure a particular angle of incidence, the relevant angle of refraction, and you are finding the refractive index by using a single measurement, sin I over sin R. Okay, how to find the uncertainty in refractive index when you measure the angles I and R by using protractor. Okay, so I and R are measured by using protractor single measurement, not multiple measurements. So their n is equal to sine I over sine R. I and R are measured by using protractor. So protractor means you know the least count 1 degree Celsius. So uncertainty will be half of it, 0.5 degrees Celsius. So I is given as the measurement of I, for example 36 degree. So it's going to be plus or minus 0.5 degree, that's uncertainty. R is equal to just 21 degrees Celsius. Sorry, not Celsius, 21 degree plus or minus 0.5 degree. Okay. So we can find the n, the refractive index, just substituting in that equation. So the refractive index n is going to be sine I over sine R, sine 36 over sine R, that is 21. So the refractive index will be equal to 1.64. So we want to find the uncertainty in n, the refractive index. What is the uncertainty? Okay, there also we find the maximum value of n and the minimum value of n first. So how to find that? N max, we need to find it, is equal to sine I max, the maximum possible value of angle of incident over the denominator R minimum. I max is equal to 36 plus 0.5 sine 36 plus 0.5 over sine 21 minus 0.5, because we need to bring the denominator smaller to get the fraction maximum, is it? So that is 21 minus 0.5. So you will get n max, that will be 1.70. Same way find n minimum. What could be the possibly minimum value of n? That is sine I minimum over sine R maximum. So sine I minimum means 36 minus 0.5. 0.5 is the uncertainty in the measurement of I and I. Same way sine R, that is maximum, that is 21 plus 0.5. So minimum value of refractive index will get 1.58. Okay, so uncertainty in n is going to be half n max minus n min. So that will be half. N max is 1.70 minus 1.58. So uncertainty in n you will get 0.06. That is the uncertainty in n. Okay, if you want to find the percentage uncertainty in n, percentage uncertainty in n, uncertainty in n 0.06 over value of n that we found in 1.64 into 100%. So that will be equal to 3.7%. Okay. Okay, so in all these examples calculating the uncertainty, we consider only one measurement, that is single measurement. Just one measurement, like initial temperature, final temperature. One initial temperature, one final temperature, we found the change in temperature. Or one angle of incident, I, one angle of refraction, sin I over sin R. Just one measurement of angle I and angle R. Or even earlier, all the examples we came across, or diameter, just one diameter. Okay, we came across just one measurement, and how to find the uncertainty of single measurement, right? I already told that when I explained about two different types of errors, I said random error. We can reduce the random error by taking repeated measurements and finding the average. So the reason for taking repeated measurements of the same quantity is to reduce the random error. I told about dropping a ball. I already explained that, right? And time taken to fall 8-meter height. We repeat the measurement because of the reaction time. The time taken will not be the exactly same. It could go more or less repeatedly when you do compared to the actual time. So we find the average time. Okay, when there is a repeated measurements, how to find the uncertainty and percentage uncertainty of this quantity? So for example, even when you are measuring a diameter of a wire, the wire, due to some technological problem, they can't make the wire exactly the same diameter everywhere. So the diameter of the wire, when you measure by using micrometer screw gauge, we need to measure the diameter at different points at different orientation. That means we can measure the diameter here, then here, rotate it and right. So like that, different orientations also we need to measure to reduce the random error. Okay, so whenever there is repeated measurement of the same physical quantity, how to find the uncertainty? Okay, so imagine a diameter of a wire is measured by using micrometer screw gauge at 5 different points, and the readings are, for example, 0.64 millimeter. The second one is 0.61 millimeter, 0.66 millimeter, 0.87 millimeter. Then the other one is 0.62 millimeter. Okay, so these are the repeated 5 different measurements of the same wire by using a micrometer screw gauge. Okay, so here you can see this all are almost the same. First decimal point 0.64, 0.61, 0.66, 0.62, but this is completely different compared to all these readings. So that means it's an anomaly. We don't need to consider it at all. We can totally ignore that value. So here we need to find the mean value, the average diameter. I told that to reduce the answer, to reduce the random error, we need to find the average or mean value. So the mean D is equal to 0.64 plus 0.61 plus 0.66 plus 0.62 over 4. So that will be 0.63 millimeter. Okay, right, that's not an issue. O-level IGCSE also you had this type of thing. How to find the uncertainty during these type of repeated measurement? Anyway, we need to ignore it totally. We don't consider it at all anymore. Right, so the second thing is how to find the uncertainty in D. So that, remember the method, half into maximum value of this, maximum measurement minus minimum measurement, that must be given in the same decimal point. All readings are given in 2 decimal point. Give that also in the same decimal point. So maximum minus minimum measurement. So half into, anyway this have to be totally ignored. Maximum, other than that, the maximum is 0.66 minus the minimum is 0.61 times half. Okay, solve it. You will get 0.03. You will get 0.025, but you have to give it with the same decimal point. So 0.03 millimeter is the uncertainty. When you are having repeated measurements, uncertainty will be different from the half of the least count of the instrument we use. We know that instrument here I told you is micrometer screw gauge. It's uncertainty for single measurement. Single measurement is 0.005 millimeter. But here, repeated measurements, we can't use the uncertainty of single measurement. So that has to be this way we have to calculate. Remember the method, maximum minus minimum reading into half. So 0.03 millimeter. Okay, so if you want to find the percentage uncertainty, in D, same thing. Uncertainty in D 0.03 0.03 millimeter divided by the mean value of D, So the denominator should be the mean value of D, 0.63 millimeter into 100%. So when you solve, in which you will get that will be 4.8%. That is the percentage uncertainty in the repeated measurement where D is the measurement. Okay. Okay, so I told first example under repeated measurement. Second example under repeated measurement. Sometimes they might say the diameter of a wire is measured by using micrometer screw gauge at 5 different points at different orientations. So the repeated diameter values are 0.42 millimeter, 0.42 millimeter, 0.42 millimeter, 0.42 millimeter and 0.42 millimeter. Okay, so here in this one the repeated measurements are given exactly the same values, but they are repeated measurements. So if you follow the same method for repeated measurement, half times uncertainty is equal to half time maximum measurement minus minimum measurement, you will get maximum minimum all same here, nothing different. You might get the uncertainty 0, but remember that according to the basic idea, the concept of uncertainty, when I start this lesson, I told at start of this lesson, what is the meaning of uncertainty, why there is uncertainty. I explained by using a voltmeter connected across two different resistors. So any measurement has uncertainty. There is no instrument with 0 uncertainty. Any instrument, anything, even data logger has uncertainty. So any measurement has uncertainty. Any measurement has uncertainty means here you can't give the uncertainty 0. So if you have repeated measurements, if it is given exactly with the same value and they are saying it's measured by using a micrometer screw gauge, means you have to take this one as a single measurement. Even though it's a repeated measurement, you have to take it as single measurement, because if you try to find the uncertainty by using half maximum minus minimum, you will get 0. All measurements have uncertainty. There is no measurement with 0 uncertainty. Okay, so here the uncertainty, you have to consider this as a single measurement. So a single measurement, it's mentioned by using, I didn't write it, by using micrometer screw gauge. Micrometer screw gauge. So its uncertainty is equal to 0.005 millimeters. So the uncertainty in this measurement is 0.00, 0.01 divided by 2, 0.005 millimeter is the uncertainty. Percentage uncertainty. So if you find the mean value, you will get 0.42. Percentage uncertainty is uncertainty, that is 0.005 millimeter over 0.42 millimeter into 100%. So you will get a value. Anyway, you can find the value. But here the important thing is, if the repeated measurements are exactly the same, don't try to find half max minus min, you will get 0. But everything, all the measurements have uncertainty. There is no measurement with 0 uncertainty. Okay, so you have to go back this as a, treat this as a single measurement. So it's a micrometer screw gauge. Least count is 0.01, half of it 0.005. That is the uncertainty of this measurement. Okay. Okay, so the third example related to repeated measurements. A student wants to measure the diameter of a coin. So he is given only just one coin or one circular disc or something like that. He wants to measure the circumference of it. So he measured the diameter of the given coin by using vernier caliper. So at different orientations. So that normally we don't know. Keep the coin between the jaws of the vernier caliper. You have to rotate the coin and measure the diameter at different orientations and find the mean diameter or the average diameter. to reduce the random error. So there he repeated 5 times sorry 4 times, and the repeated measurements by using a vernier caliber 12.1 millimeter, then 12.3 millimeter, 11.8 millimeter, and 12.2 millimeter. So the aim of the experiment is to find, the aim of the experiment is find the circumference. Find the circumference, that's the aim of it. Not measuring the diameter, but he can't measure the circumference without measuring the diameter. So he is going to find the circumference by using the equation 2 pi r or pi d. But he had 4 different repeated measurements. Okay, here we had to find the circumference, so that's not an issue. We'll find the mean value of d, and c is equal to pi into the mean value of d. We'll get the circumference. That's a normal way we do. But how to find the uncertainty in circumference, the measurement or the value of circumference? How to find the uncertainty and percentage uncertainty? That's this example. Okay, so here we can find the mean value of d equal to 12.1 plus 12.3 plus 11.8 plus 12.2 divided by 4. So that will be equal to 12.1 millimeter. Okay, so the circumference C is equal to pi into d mean value. So that's going to be pi into the mean d is 12.1 millimeter. So that will be equal to 38.0 millimeter. Okay, so I need to find the uncertainty in C, the circumference. How to find the uncertainty in C means, we know how to find the uncertainty in D. Uncertainty in D, we find it by using half maximum minus minimum. That is uncertainty in D. Is it repeated measurement? So uncertainty in D is half into max minus min. And already told that when we find the answer, after finding the uncertainty in D, how to find the uncertainty in C means uncertainty in C is equal to pi times. So we are measuring the D by pi. So we are measuring the, we are multiplying the value of D by pi to get the circumference. So the uncertainty in C is also, how to find it? Uncertainty in C is equal to pi times uncertainty in D. Uncertainty in C is equal to pi times uncertainty in D. Here the D is the mean value. It's multiplied by pi to get the circumference. Means to find the uncertainty in C also, earlier also I told, if you have a measurement, if you multiply or divide that measurement by a number, uncertainty also will be multiplied or divided by the same number. So here D is not a measurement, but it's average measurement. It's multiplied by pi to get the uncertainty means, to get the circumference means, the D is multiplied by pi to get the circumference means, to get the uncertainty in C, we should multiply the uncertainty in D by pi. Okay, so we can say that, write it like this: uncertainty in C is equal to pi times in D. But uncertainty in D, we know how to find it. Half max minus mean. Maximum is 12.3. Minimum is 11.8. So that will be 0.3 millimeters. So uncertainty in C, because we multiply D by pi to get the C, means uncertainty of C is also pi times uncertainty in D. So that is pi into uncertainty in D. So I already mentioned that, no? Yeah. So that is pi into 0.3 millimeter. So that will become 0.94 millimeter. Percentage uncertainty in C, you can divide this by 38 point and find that's the percentage uncertainty. Okay. Okay, so the next topic is percentage difference. Why do we find percentage difference? We find percentage difference just to check how much a particular experimental value is deviating from, at what percentage is it deviating from the actual value if you know the actual value. Say for example, a student measured the gravitational acceleration by using a free fall apparatus and he got a value of G. The experimental value of G is 9.68 meter per second squared. We know the actual value 9.81. So what is the percentage difference between the experimental value and the actual value means? We find like this percentage difference. We can shortly write percentage sign with capital D, difference over. So that's just difference. So we know the actual value 9.81 minus 9.68 over actual value, that is 9.81 into 100. Normally it must be given in 2 SF, two significant figures. So that will be 1.3 percentage. 1.3. Right. That is one example regarding percentage difference. Percentage difference could be found by using, percentage difference we can find in this type of situation also. Say for example, it's like this, you are given two different identical coins, right, same value of coins, say 5 rupee or something like that. You are given two different coins and you are trying to find out whether they are made of same material. So you found the, experimentally you measured the density of the two coins separately, but you don't know the actual value of the density of the coins. Here we know the actual value of the G, 9.81, so difference over actual value into 100. Since we know the actual value, or if you know the theoretical value of a particular quantity. But here in this experiment, second example, this is the first example. The second example where we find the percentage difference, say you are trying to find out the density of two different coins. It looks like same type of materials, but you found the density of the first coin 1.62 gram per cm cube. The second coin you found the density of it is 1.74 gram per cm cube. Okay, so what is the percentage difference between the density of these two coins means? We need to find the difference, same as here, difference over. Here we know the actual value, but we don't know the actual value. So the denominator should be the mean value of the two densities. So that is mean value we need to find, that is 1.62 plus 1.74 divided by 2. So that will be 1.68 gram per cm cube. So percentage difference in density, difference over, that is 1.74 minus 1.62 gram per cm cube divided by the mean value 1.68 into 100. So that will be equal to 7.1 percentage. Okay, so if we know the actual value or theoretical value, that must be the denominator. Since we don't know the actual value, we find the mean value and that will become the denominator. Okay, I put the heading shortly. That's the last part of this error calculation. Now, when you are doing a practical, why do we do practical? To find a particular physical quantity, value of a particular physical quantity. So, at the end of the experiment, we need to give the conclusion whether our experimental value is acceptable, because each and every measurement has uncertainty. It's not an error. I already told that uncertainty and error are different. Uncertainty because of the instrument you use, the instrument is unable to measure more precisely than its least count. So because of that there will be uncertainties, all I told that. Okay, at the end of your experiment you are getting a particular value for a measure for a particular physical quantity. Say for example, you did a practical to find the gravitational acceleration by using a free fall apparatus and you got a value of g. You got a value of g, the first example. You got a value of g which is 10.27 meter per second square, and your experiment has a percentage uncertainty of 4.9%. That's a percentage uncertainty in your experiment. You used a meter rule to measure the height it's falling and everything. I don't need to tell all the methods again, and certain methods are in unit 6 if the index is there anything. But you might get a question like this. A student did an experiment to find the gravitational acceleration and his measure and his experimental value is 10.27 meter per second squared, and the percentage uncertainty is 4.9% in his experiment. Okay, so 10.27 is not equal to 9.81. 9.81 meter per second squared is the actual value, but your value is 10.27, more than the actual value. So I'm going to say, I'm going to conclude my value, my experimental value is more than the actual value, which is 9.81. So my experimental value is not acceptable. I'm going to say that. Or I'm going to say that my value is closer to the experimental value. I'm going to accept it. No, you can't give conclusion like. There's a method. There's a proper scientific method to decide whether my experimental value is acceptable or not. You must know that there are questions in the past paper, right? So how to decide? There are two different approach we can do. First approach, method 1, we know the percentage answer which is 4.9%. Okay, so the first method we can find the uncertainty of your experimental value. So uncertainty in G, the value of G 10.27 meter per second squared into the percentage divided by 100. So you will get the uncertainty of your value is 0.50 meter per second square. So your experimental value G is equal to 10.27 meter per second square plus or minus 0.50 meter per second square. Okay, we'll find the range of your value, range of experimental G. G means gravitational acceleration is 10.27 minus 0.5, that will be 9.77. That 2, from this to 10.27 plus 0.5, that is 10.77. Right. But the actual value of G is 9.81. Actual value of G, we know that okay, then check the actual value. Is it falling within the range of my experimental value? If it falls within the range of my experimental value, then I can conclude my experimental value, that is 10.27 meters per second squared with this percentage uncertainty, or 10.27 meters per second squared with this uncertainty is acceptable. Okay, so you can check that 9.81, is it falling within this range? Yes, this 9.81 is falling within the range of 9.77 meter per second square to 10.77 meter per second square. That is the range of my experimental value. So 9.81 is falling within this range, means my experimental value, which is 10.27 meter per second square with this percentage uncertainty or with this uncertainty, is acceptable. That's a conclusion you should say. Experimental value is acceptable with this percentage uncertainty because the actual value is falling within the range of my experimental value. Okay, this is the first approach. Okay, so the second method, what to do? First method I already told that find the range, check whether the actual value is falling within the range of the experimental value. Second method, find the percentage difference between your experimental value and the actual value. I already told how to find the percentage difference. So find the percentage difference between your value and the actual value. Percentage difference is equal to difference, that is 10.27 minus 9.81 over 9.81 into 100%. So the percentage difference will be equal to, you will get 4.7%. Yes, 4.7% is the percentage difference. Okay. Now the theory says that's the reason you don't need, but according to the proper theory of this error calculation, if the experiment there is no mistake or anything, then percentage difference cannot exceed the percentage uncertainty of the experiment. That means if it is a correct experiment where if we are able, if we decide that we can accept, means the percentage difference must be less than percentage uncertainty. So here we know that percentage difference between your experimental value and the actual value is 4.7. So you found the percentage difference. Check with percentage uncertainty, which is given as 4.9%. If the percentage difference is less than percentage uncertainty, the idea, the percentage difference cannot exceed percentage uncertainty if the experiment is done properly. So here percentage difference is not exceeding the percentage uncertainty, or percentage difference is less than percentage uncertainty. Therefore, since percentage difference less than percentage uncertainty, the experimental value is acceptable. Value of G is acceptable. So one of the methods you can follow, the final conclusion will be the same for both methods. Okay, first method, you find the range of it and check whether the actual value is falling within the range. The second method, find the percentage difference. Here percentage uncertainty is directly given, but if they give the uncertainty of it, instead of percentage uncertainty, they give an uncertainty 0. We found the uncertainty 0.5. Say the same thing could be given as 10.27 plus or minus 0.5. Then percentage uncertainty you find it. Uncertainty if they give instead of 4.9%, if they give something like this, G, the experimental value of G is equal to 10.27 meter per second square plus or minus 0.50 meter per second square. Then find the percentage uncertainty, that is 0.50 divided by 10.27 into 100%. You will get the percentage uncertainty. I think you will get 4.9% there. 4.9% you will get it. Same thing you will get it. What is given you will get it. So percentage uncertainty, percentage difference you find it. Compare both. Percentage difference less than percentage uncertainty means it is acceptable. Okay. That's the second method we follow. Okay, the second type of question that could come under this determining the conclusion. They might give the, say, maybe they might say a student measured the density of a particular coin which is made of a metal, and experimentally the student got the density. They might say density is equal to 2.94 gram per cm cube plus or minus. Uncertainty also given as a percentage answer to 7.2%. Okay, so the answer is given as percentage answer 7.2%. Right. Now the question is, they are not giving any actual value or anything, but they are giving different type of materials, and the aim of this question, you need to identify this coin where the student used to find the density. This coin is made of which material? They might give a table, something like material and density, something like this. Density rho, gram per cm cube. The name of the materials, they might say, I'm not just giving any specific name, I'll just put the name of the material A, B, C, D. The material A, its density is 2.64. Material B, the density is 2.75. Material C, the density is 3.21. And D, the material, that is 3.27, all gram per cm cube. So this coin, where the student used to find the density, its density is 2.94 gram per cm cube with a percentage uncertainty 7.2. So this coin made of which material you need to identify in terms of density only. Okay, so there you need to find the uncertainty of the densities because you are given percentage uncertainty. Then after you find the uncertainty, find the range of the experimental value for the coin, but the student used to measure the uncertainty. Find the uncertainty first, then find the range of the density, then check which density is falling within that range. Which density, the given density, is falling within the range of the experimental value of the coin density, then that will be the material. Okay, not an issue. So we'll find the uncertainty in density for the student's experiment. So that is 2.94 into 7.2 over 100. So that is better to give it in 2 decimal points. So there you will get 0.21 gram per cm cube. So including the uncertainty, the density of the student's measurement, that is 2.94 gram per cm cube plus or minus 0.21 gram per cm cube. So the range of the experimental value of the density for the coin will be 2.73, 2.94 minus 0.21, that is 2.73 gram per cm cube to 3.15 gram per cm cube. This is the range of his experimental value for the density of the coin, right? But these are the materials with standard density A, B, C, D. Okay, now which density of these, out of these 4 materials, which density is falling within this range? If you check it, you can see only B, 2.64. This is lower than 2.73, so this is not falling within the range. 2.75, yes, it's falling within the range. 3.21 more than 3.15, 3.27 also more than 3.5. So the material used by the student, so the material of the coin is B. They might give iron, steel, whatever it is, but I just use A, B, C, D. The coin is E because that density is falling within the range. It's a normal question, comes several times, it came in the past papers. Okay, so these are the error calculations in unit 3, but there are more error calculations, but they are in unit 6. For example, when 2 measured quantities are multiplied or when 2 measured quantities are divided, how to find the uncertainty and percentage uncertainty of that quantity. For example, you know the speed equal distance over time. Student is measuring, the students want to measure the speed of a trolley, so he measured the average speed of a trolley, so he measured the distance moved by the trolley and the time taken for that particular displacement, and he is dividing the displacement by the time or distance by the time. If it is moving on a straight line, distance and displacement will have the same magnitude, and he calculated the speed. So how to, the uncertainties are in both measurement of distance and measurement of time. How to find the uncertainty of speed? Yeah, that is in unit 6. Or maybe something like whenever there's an index comes in the measured quantity. For example, you know that area of a circular surface or area of a circular surface is given by area pi r squared or pi d by 2 squared. So there's an index comes to. So pi is a number. D is the measured quantity. D is the measured quantity. That measured quantity has uncertainty. If it is measured by using vernier caliper, there will be an uncertainty of 0.05 millimeter. How to find the uncertainty in A? That also in Unit 6 mostly. But during the last 5-year paper, there are no such questions in Unit 3. They appeared in Unit 6. So I am not going to discuss them. Those who are interested, you can see the Unit 6 video. I already uploaded it. I'll give the link in my description. Maybe sometimes something like when two measured quantities are multiplied, say volume of a cylinder is given by pi d by 2 all things squared into h. So h is a measured quantity, d by 2, d is a measured quantity with the index 2. So d and h are multiplied, both d and h has uncertainty because they are measured quantities. How to find the uncertainty in volume, that also in Unit 6. Okay. So these are the error calculations mostly related to Unit 6. In the recent papers, Unit 3, there are no such questions. Okay, so I am not discussing it in Unit 3. Those who are interested, you can watch my Unit 6 error calculation video. Okay, so the next topic I am going to discuss related to certain techniques in experiment, or certain experimental techniques I am going to discuss now. Okay, the first technique, whenever you measure the height of an object above a table or above a ground, for example, in this experiment, the student wants to measure the height of the mass attached to the trolley. So, what's the initial height? Due to some experimental purpose, maybe something like he wants to calculate the loss in GP, something like that. Okay, whatever it is, he wants to measure the initial height of the mass attached to the trolley, right? So, there we are using a meter rule. So the meter rule should be kept possibly closer to the mass, and we use a set square S1. It should be attached with the ruler to ensure the ruler is vertical. So the set square S1 is used to ensure the ruler is vertical. So the set square has to be held like this. The second set square is used to take the reading. So the reading, the height could be measured because when the mass falls down, the bottom is going to hit the ground. So we need to measure the height from the bottom here. We don't consider the dimension of the object because mgh, h should be from the center of mass. But anyway, we are not considering that because the dimension of the mass attached is very small. So we are going to measure the height of the bottom of the attached mass above the ground. So when you are taking the reading, the ruler, the zero of the ruler should be kept at the lowest point. The zero of the ruler should be kept at 0 point. When you are taking a reading, the second set square is used to avoid parallax error. To avoid parallax error, the second set square S2 is kept such that it touches the bottom of the mass. So this technique you must know. They asked in the past papers, draw a diagram where the height of the mass above the ground, how the student can measure it. Okay, so this technical experimental technique, you must know this. Okay, so second technique, how to measure the thickness of a thin sheet, something like a paper, normal writing sheet, how to measure the thickness of it. If you have many identical sheets, keep all the sheets together and measure the total thickness by using micrometer screw gauge and divide by the number of sheets you use, because the larger the measurement, lower the uncertainty, percentage uncertainty. I already explained it. So if you have many identical sheets and your aim is to measure the thickness of a sheet, measure the total thickness of several sheets, maybe 50 or 75 or like that. Keep all together, remove the air, press it, remove the air layers between the sheets and measure the total thickness and divide by the total number of sheets. You will get the thickness of a sheet. Okay, but if you don't have many sheets, there also you have to use a micrometer screw gauge. Is the best instrument because the resolution is smaller, so the uncertainty of the measurement is smaller. When you divide by the number of sheets, the uncertainty and the percentage uncertainty also will become very small. That's the advantage. We need a smaller range. Finally, when we write the final conclusion, we need a smaller range. I already explained those things in the previous section when I discussed about error calculation. Okay, but if you don't have many sheets, for example, you have only one sheet, means fold it into several times. Say if you fold it once, the number of sheets will be 2. If you fold it second time, the number of sheets will be 4. When you fold it again, the number of sheets will be 8. When you fold it again, there will be 16. Like that, fold it several times, press it and remove the air, and measure the total thickness by using micrometer screw gauge and divide it by. There also, when you measure the thickness, you should measure the thickness at different points. Even earlier what I said, when you are measuring the thickness of several sheets also by using micrometer screw gauge, you must measure it at least 4 different points and find the average thickness and divide by the number of sheets. Here you need to measure after you fold it maybe 5 times or whatever it is, measure the thickness at least 4 or 5 different points, find the average thickness and divide it by the number of layers of sheets you got when you fold it, right? That's a technique you must know to increase the, to reduce the uncertainty and percentage uncertainty in the thickness of the sheet. That techniques you must know. Okay, so next thing is measuring the diameter of a coin or diameter of a small disc. If you have only one coin and if you have a vernier caliper, you can use the vernier caliper to measure the diameter, keep the coin between the two jaws like this and measure the diameter, then rotate the coin and measure the diameter at different orientation and find the mean diameter. If you have one coin and a vernier caliper, you can measure it like as shown in figure 1, rotate it and measure the diameter at different orientations. Okay, but if you have just one coin but you don't have vernier caliper, what to do? You can measure the diameter by using 2 set square and a ruler. Keep the coin like this between 2 set squares on a white sheet. So keep the white sheet on a horizontal plane, keep the coin in a vertical plane and keep 2 set squares as shown on the diagram and mark the edge of the set square first one and the second one which is touching the surface of the coin. Then measure the distance between the two edges. You can mark a small line on the white sheet that shows the edge of this side and this edge of the set square. Then measure the distance from this line to this line by using a meter rule when you have only one coin and a ruler. You don't have vernier caliper, right? If you have vernier caliper, you can measure the diameter like this. Don't use a micrometer screw gauge because using micrometer screw gauge will give a wrong value. There will be a big systematic error because when you keep the coin between the two jaws of the micrometer screw gauge, the problem is we don't know whether we are keeping along the center of the coin. Sometimes we might keep it like this also we might keep it. So it's difficult to keep it along the diameter. So using a micrometer screw gauge to measure the diameter of a coin is not an advisable, better don't use it. Right. If you have many coins and meter roll, many identical coins at a meter roll, you don't need to measure this way. You can keep all the coins on a white sheet next to next, right, as shown in the diagram, and measure the total length from first edge to the last edge. Measure the total length by a meter rule and divide it by number of coins. That will give the diameter of a coin. Or if you have micrometer screw gauge, you can find the diameter, if you have vernier caliper, you can measure the diameter of this coin as shown here, then measure the diameter of this coin, this coin, this coin. Whenever you measure the diameter of a coin, you have to measure it's at different orientation. Find the overall average of all the coins. That will be the best method. But if you don't have vernier caliper and if you have ruler, you can keep all the coins like this and measure the total length and divide by the number of coins. You will get the average diameter of a coin. Okay, when you take a reading, a length by using a meter rule and you are giving the final answer in meters, means you must give it in 3 decimal points. When you are using a meter rule and when you record the length in meters, you must give it in 3 decimal points because meter rule means the total length is 1000 millimeter because 1 meter rule means 1000 millimeter. When you divide it by 1000, it's going to be 1.000 meter. So for example, sometimes students they say length of something is 46.4 meter. 46.4 meter they say. Sorry, I mean to say. They say something like 0.46 meter. But actually, it's not 0.46 meter. One decimal point you can include it. In millimeter, if you write the same thing, that will be 0.4. In millimeter, if you write it the same length, it will be 460 millimeter. Divide by 1000, you will get 0. If you divide it with 1000, you will get 0.460 meter. Okay, so whenever you are writing length in by using a meter rule, it must be given in 3 decimal points. Say for example, you can't say a particular length is 0.63 meter. It's not accurate because you are giving it in 2 decimal points. You say that you measured a length by using a meter rule and the length is 0.63 meter is wrong. Maybe it might be 0.631 meter because when you convert this to millimeter, there will be 3 decimal points, or maybe 0.630 meter. So always when you take a length by using a meter rule and when you are writing it in meters, the answer should be given in 3 decimal points because the total length is 1000 millimeter for a meter rule. So remember that, give the answer in 3 decimal point. Nearest millimeter normally we say. So 3 decimal points you can give the measurement when you take by using meter rule. Okay, so next technique, how to measure the height of a roof or height of a building, height of a roof of your laboratory. It's actually not 100% accurate, but it's an estimation. Normally, we can accept this method or procedure to measure the height of a ruler. So what we do, for to measure the height of the roof from the ground, keep a meter rule such that it touches the wall and the ruler should be kept in vertical position. By using a camera, take a photograph. On the photograph, you should be able to see up to the roof and clearly from the ground the height of the meter rule. You should be able to see it on the photograph. Say for example, this is the photograph. In the photograph, you must be able to see the roofs. The roof is here and you see the meter rule here. Right. So this is a photograph. So, after taking the photograph, measure the height of the ruler, which is actually 1 meter. What's the height of the ruler in the photograph? Measure that height. Let it be h. Then measure the height of the roof from the ground. That is h1. We can calculate the height of the roof by using a method. That means actual height is 1 meter, that is shown in the photograph by a height h. That means h indicates 1 meter. H is the height of the ruler in the photograph. That is actually 1 meter. So h indicates a height of 1 meter. So 1 meter will be indicated by 1 over h meter. So 1 meter is equivalent to 1 over h meter actually. Now the height of the roof is h1. Height of the roof is h1 in the photograph. You can measure it in centimeter. It's okay. Height of the roof is h1, right? Height of the roof is h1. So height of the roof is h1 means what will be actual height of the roof means? Actual height of the roof means we can use the estimation like this. H meter indicates 1 meter. That means 1 indicates, that is 1 unit or 1 centimeter. Maybe when you measure the height of the meter rule on the photograph, it could be certain centimeter, h centimeter, right? It's okay, h centimeter indicates 1 meter height. So 1 centimeter indicates how much of meter, that is 1 over h meter. Now when you measure the height of the roof, that is h1 centimeter. So h1 centimeter means how much of meter? That's going to be 1 over h into h1 meter. So that is the height of the roof. So the height of the roof is going to be h1 over h meter. h1 over h meter is the height of the roof in meters. It's actually not 100% accurate, but it could be an estimation. Okay, so the next technique, how to measure the speed of a small sphere, something like marble. For example, a student is trying to do some experiment related to momentum. So he should know the speed or average speed of a marble before collision. Okay, so the method, sometimes if the distance moved by it is smaller, we won't be able to use stopwatch. So there we can use video camera. We can use a video. So there what we do, video it. Let the marble to move in front of a meter roll. So the scale of the meter roll should be clearly visible. The marble is projected just closer to the meter roll. So video it perpendicular to the meter roll. So you know the position of the marble clearly in front of the meter roll. Okay, video the motion of the marble, right? You know, normally the cameras, they tell the frame rate, that is number of frames per second. You can get it any camera in video. So you know the frame rate, that is number of frames per second. So from that we can find how much of time taken for one frame to move, right? So we know the distance moved by a marble from this point to this point. We can measure the distance moved by the marble since the marble is moving in front of the meter roll, and you can calculate how many frames it has taken to move from this point to this point. For this video, how many frames are there for that particular motion of the marble. Okay, so since we know the number of frames, so for example, we can say how many the frame rate. Say for example, for a camera, if the frame rate is 30 frame per second, means in 1 second it shows 30 frames. So one frame belongs to the time of 1 over 30 seconds. We know the time taken for one frame. So we know the distance moved by the marble from this point to this point. We can read it from the meter roll. Say for example, if the distance moved here, we know that. Say for example, if it is 40 centimeters. So the speed is, and there are, for example, there are 12 frames are there. 12 frames are there. So the time taken by the marble to move from this to this, the total time is equal to 12 times now 1 over 30 seconds. You know the time. Just example I am taking it. So that's the time taken for the marble to move from here to here. So we can find the speed is equal to distance over time. We know the time. Just I took an example, not a correct example. Time we know, number of frames into time for one frame to move, that is 1 over 30, because the frame per second is 30. In 1 second 30 frames are taken. So we know the time, we know the distance moved by it. So from that we can find the average speed is equal to distance, that is 40 centimeter divided by the time. From that we can find the average speed of the marble before collision. Okay, so when you are measuring the angle of a slope, you are trying to do a practical related to motion of a trolley on a ramp or motion of a marble or something on a ramp, you need to measure the angle. Means don't use a protractor. I already calculated the least count in my error calculation part. If you are using a protractor, the angle, the smallest angle that could be measured is 1 degree. But if in this method, if you are using trigonometry, what you do? Measure the height of the edge of the ramp. You use a known length of ramp. For example, if it is 1 meter, the length of the ramp is 1 meter. So there, you know the height of the ramp. So if, for example, for a particular experiment, you are varying the angle. So at a particular angle theta, you are going to measure it. So keep the angle theta where you want that and measure the height, measure the length of the ramp, that is I just took it as 1 meter. So then use the equation sine theta is equal to d over L. From this find the theta sine inverse. Don't use a protractor. So to measure the angle, don't use a protractor, measure it by using meter rule by using the trigonometer. Don't use a meter protractor because the least count is just 1 degree. Here you can go up to much smaller, 0.057, I think, very small angle you can go up to that least count. So this is the very high resolution method to get the measurement of angle. Higher resolution means you can get very small angle. The value I didn't say high. High means here a very small angle could be measured by using this method. Okay, so you are doing an experiment related to equilibrium condition for equilibrium means where if you want to measure the angle theta, these are the two light strings. This is a Newton meter, this is a known weight attached to it. Student wants to measure the angle theta. So here to measure the angle theta, don't use protractor because difficult to hold the protractor such that to measure the angle. So angle of slope of this string. Here also you must use a ruler. You can use a meter rule, something like this. In front of it, keep a meter rule, something like this. This is the table, so up to the table, keep a meter rule, something like this. And keep a set square to ensure the meter rule is vertical. So measure this height from the above the table up to this point, measure the height of it, let it be h1. So that is h1 is this height. Then at a known distance somewhere here, keep another meter rule, second meter rule in front of it, and use a set square to ensure that meter rule is vertical. So you must know the distance, horizontal distance between the first position of the meter rule and the second position of the meter rule. This distance you should know, let it be d. Then measure the height of this point above the table, let it be h2. So I know this height. So this height is h1 above the table. This height is h2 above the table. So this height, so I would use trigonometry. This height is h1 minus h2. This distance between these 2 points, this distance I know I measure it here. That is d. Then use the angle tan theta. Tan theta is equal to h1 minus h2 over d. From this you can measure the slope of that string. Okay, that's the technique you should use to measure the slope of a string when you are doing a practical like this. Also, in this experiment, student must keep this string in a horizontal position. Due to some reason, he wants to keep the string in a horizontal position. How can we confirm the string is in horizontal position? Okay, so at the edges, measure the height again. Measure the height of the string above the table, somewhere here. Keep a ruler and measure the height with the support of a set square. So record the height of this position, let it be for example h3. Then measure the height somewhere here because you want to confirm the string is horizontal. Measure the height again here. I'll remove this ruler, that part is over. So measure the height of that string somewhere here with the help of set square. And measure this height. If it is h4 which is different from h3, that means the string is not horizontal. So you have to adjust this position of the string balance up or down until this reading also becomes h3. If both readings are the same, the height of this one and height of this one same, these are the meter rules. If they are same, that means the string is in horizontal position. This is the technique we use to confirm a string is or something is in horizontal position. We measure the heights at two different edges or two at extreme position. If the heights are the same, that means it is horizontal. Okay, so in Unit 2 we learn about wave particle duality. Electrons have wave nature when the accelerated electrons pass through graphite. So this is called electron diffraction tube. This is a zinc sulfide stream when the electrons pass through the after passing through the slit. That means the electrons are accelerating from cathode to anode, and accelerated electrons when they pass through the graphite film, they diffract and overlap and form concentric circular rings on the zinc sulfide screen. So I drew the pattern what could be seen on the zinc sulfide screen, which is a curved screen. Separately I drew it, and you want to measure the diameter of a particular ring. Okay, to measure the diameter you can't use a meter rule because meter rule can measure only a straight lines, is it? So if you keep a meter rule something like this on the curved track, if you keep a meter rule, you can't keep it because a ring is starting from here and ending at here. Means if you try to keep a meter rule, the meter rule will touch at the center and those two ends will be just flying or just not touching. You can't measure the diameter of a ring by using a meter rule. For that you should use a vernier caliper. The two jaws of the vernier caliper should be kept like this. So you can open the vernier caliper and you can keep the vernier calipers to jaws at the edge of the ring, something like this. Difficult to draw, but I'll try to draw. So one edge should be kept here like this, and the other edge should be kept like this. So by after that, I'm not drawing the other part. Vernier caliper is somewhere here, the balance part is somewhere here, right? So keep the vernier caliper like this and take the reading as usual by using the vernier caliper. So vernier caliper is a suitable instrument to measure the diameter of the ring, which is formed on a curved zinc sulfide scale, because the two jaws will touch exactly on the opposite ends of the circular ring along a diameter, and you can measure the diameter. So if you can't use a ruler, because ruler, when you keep it, the center part will touch the ruler, and you can't keep the ruler such that where you are going to take the readings at those ends, the ruler will not touch, so we won't be able to measure the diameter. So to measure the diameter, vernier caliper is a suitable instrument here. Okay, next I am going to discuss some experiments in which the equations could be given to you, the equations related to the experiments. For example, the first experiment, measuring the gravitational acceleration by using free fall apparatus. So you should be able to rearrange the equation s equal ut plus half at square we use. There you should be able to identify the dependent variable, independent variable, and you should be able to rearrange the equation such that you get a linear equation. Say for example, the graph for linear graph y equal mx, or y equal mx plus c, or y equal mx minus c, or y equal minus mx plus c. These are the standard 4 equations related to linear graph. So we should be able to rearrange the equations into one of these formats, and by using the graph we should be able to find the unknown. So students sometimes have problem rearranging the given equation into a proper linear graph equation, y equal mx, or y equal mx plus c, or y equal mx minus c, or y equal minus mx plus c. One of these formats we should be able to rearrange the equation. Okay, so the first experiment I am going to discuss how to measure the gravitational acceleration by using a free fall apparatus. So I am not going to draw the free fall apparatus. So you know the free fall apparatus is something related to electromagnet, and the ball will be held here, and we should be able to measure the height of the ball above the trapdoor. So this is the trapdoor, and you know the standard experiment, the ball hits the trapdoor, the timer will stop. So when the ball starts to fall, the electronic timer, I am not drawing the full diagram, they don't ask to draw the diagram, but the height must be measured by using meter rule. I already told how to measure the height by using meter rule. You have to keep the meter rule, set square, everything I already explained, so I am not showing those setups here. Only the purpose of this topic is how to rearrange the equation. That's the main topic, how to rearrange the equations, which includes dependent variable and the independent variable, into one of the equation for linear graph. Okay, that's the purpose of this topic. So the height should be measured h. So you can vary the height. When the ball hits the trapdoor, the timer will stop. When the ball is released from the electromagnet, the timer will start. When it hits the trapdoor, and when the trapdoor opens, the timer will stop. So the reading of the timer is the time taken to fall from here to here. You can vary the height h. So there we are going to use the equation s equal ut plus half at squared. So the ball is released from rest, means u is going to be 0. So s equal half gt squared. So s is the independent variable. Independent variable means the variable that could be changed by the experimenter. That is called independent variable. Time is the dependent variable, because when this changes, this also changes. That is, time depends on s. So when you are plotting a graph, normally the independent variable should be on the x-axis and the dependent variable should be on the y-axis. That's a standard way of drawing the graph. So t squared should be on the y-axis. So t squared is going to be 2 over g s. So this is in the form of y. This is in the form of gradient, because gradient means it should be a constant. G is a constant. This is going to be the independent variable, that is the x. When you plot a graph of y-axis t squared, x-axis the height, so height is h, I put h, right, that's a height, h. You will get a straight line through the origin. Find the gradient. When you find the gradient, you should not use the points that you put in the graph. You have to take two other points from the graph, and you have to show the right angle triangle clearly. So you know the y2 minus y1 over x2 minus x1 is the gradient. So you know the gradient. The gradient will be equal to 2 over g. So the g is equal to 2 over m. From this you can find the gravitational acceleration of the or free fall, acceleration of free fall. Okay, the second experiment we are going to use a principle of moment to find the mass of an unknown object or unknown mass by using a known mass m0. So first the meter rule, this is a meter rule. Meter rule should be balanced on a knife edge or fulcrum. So that will be balanced at the center of mass of the meter rule. Is it? The meter rule will balance exactly at the center of mass of it. Then attach a known mass at a known distance x0, and the unknown mass should be kept on the other side, and change the distance of the unknown mass x from the position of the center of mass of the ruler. Adjust it until the ruler balances on the fulcrum. When the ruler balances, we know according to the principle of moments, we can say that clockwise moment equal to anti-clockwise moment, that is m0 g times x naught is equal to mg times x. So g and g get cancelled, m0 x naught is equal to mx. Okay, so here we are going to vary the x naught. So the known mass will be kept at different known distances, and we change the position of the unknown mass from the center of mass of the ruler. So the ruler should be always kept at the center of mass of it. So center of mass of the ruler, from it the position of the m will be varied when this position x naught is varied. So here the variables are x naught and x are the variables. So when x naught is varied, x is varying. So I am varying the x naught, then I vary the x. So here the x naught is the independent variable. Make that x axis. This should be the y axis. So x is going to be m naught over m into x. Okay, so this is in the form of then. So I think this this is x naught is equal to x is this is the independent variable x naught. So I think x naught is the independent variable. When I vary the independent variable, x is varying. So that means x should be equal to this. X should be equal to m naught over m into x. X naught. Okay. So this is the independent variable that should be on the x axis. This is the dependent variable that should be on the y axis. So x means, so I can name this, if you have confusion, this is d, this is d naught. So easy, d naught. So that's going to be, this is d naught, and this is d, the distance. D, this is d naught. X naught and x will get confused. So it's going to be d is equal to, this is d naught, right? So this is going to be on the y axis. This gradient is going to be mass m naught over m is the gradient. This is the x axis. So I can say the known mass m naught, unknown mass m. So m naught over m is, make this also giving confusion again, the gradient m. So make this unknown mass m1. Okay, then problem solved. This is m1. This is m1, right? So the gradient of the graph is going to be, when you plot a graph, you will get a straight line through the origin. The gradient of the graph will be, you'll get a straight line. Take two clear points and find the gradient. When you are finding the gradient, you have to draw the right angle triangle. So the gradient of the graph, which is m, is equal to m naught over m1. So m1 is the unknown mass. So m1 is going to be m naught over m. M is the gradient, m naught is the known mass. From this we can find the mass of the unknown object, which is m1. Okay, so we can measure the gravitational acceleration or the acceleration free fall by using air track, glider, light gate and timer. The experiment is we attach a air track through a smooth pulley to a known mass M. This is actually a weight slot. So the mass of the weight slots may be 50-gram weight slots, or you can use 20-gram weight slots. Okay, initially we keep all the weight slots here. Let the trolley to move from rest, so the friction is negligible because it's moving on air track. So when the glider moves through a known distance L, so the light gate is kept at a known distance L. When the glider passes through the light gate, the interruption card will block the light of the light gate, and the time will measure the interruption time. So the speed of the glider at a distance L from its initial position, we can find the speed by using speed is equal to L over T. The glider will be allowed to move from rest always from the same distance L, right? So here the total mass should be kept constant. Total mass means total mass of the glider and the attached weight slots, that is m naught is the mass of the glider plus m, let it be capital M, that we keep it constant throughout the experiment. So I told we start with 20-gram weight slots, maybe there are 10 weight slots are there, so totally 200 grams. So we remove a weight slot from it and we have to keep it on the glider. So we can use a small Bluetooth and keep it on the glider always. The Bluetooth should be kept initially there, so we can keep these weight slots on the glider such that the total mass remains unchanged. Okay, so if you think about the equation for the total motion, say for this one, mg is the downward force, upward force tension is equal to ma. For the glider, that is the only force acting on it is the tension. Tension is equal to m naught a. So when we add both, we will get mg is equal to T and T will get cancelled, m plus m naught times a, but m plus m naught is kept constant, that is the total mass of the system. So mg is going to be capital M a. Okay, m is the total mass. We keep the total mass constant throughout the experiment. So we change the symbol m. M is the mass of this attached weight slot. So we remove the slot by one, and every time we measure the speed when it passes through the same distance L. So whenever we remove a weight slot, that should be kept on the glider to keep the total mass constant. So here we can rearrange this equation. So A is equal to mg over m over capital M into g. Okay, so the the glider is starting from rest and it's moving through a known distance L. So v square is equal to u square plus 2as if I use. So v square we measure by using light gate and the interruption timer. So that is d over t. So we know the v square. U square is 0. We always release the glider from rest. So v square is equal to 2 times. Instead of a, I can substitute m over capital M g, and the distance it moved is always the same, that is L. Okay, so rearrange the equation. So here we are going to vary the m, the mass of the weight slot is the independent variable, the speed is the dependent variable. So we can rearrange the equation. V squared is equal to 2g L over capital M into small m. Small m is the independent variable, the mass of the weight slot. Now it's going to be a graph. We are going to plot a graph of v squared against m. So this is going to be on the y-axis. This is going to be the gradient m. This is going to be on the x-axis. So when you plot a graph, you will get a straight line through the origin. So that is v squared against m. M is the mass of the weight slot. It will be a straight line through the origin. Find the gradient. So the gradient, that also m or m naught, we will call the gradient m naught, or m is the gradient, that is going to be 2g L over capital M. So our aim is finding the gravitational acceleration g. So g is going to be m is the gradient. Careful, m is the gradient. Here also m, don't get confused. This is the, we'll change it. This m and m not always problem. So we'll say this variable mass m naught, then it, so that I already used it m. Okay, it's okay, no problem. We'll keep it like G is equal to m is the gradient times the total mass of the system divided by 2L. From that we can find the G. So that is G is going to be, the gravitational acceleration is going to be, yeah, yes, that's right. That is 2, yeah, that's right. This is going to be the G, the gradient times capital M over 2L. Yes, that's right. So from this we can find the acceleration of free fall. Okay, so the next experiment is verifying the law of conservation of momentum by using air track and glider. So here both gliders must have exactly the same mass. If the masses are slightly different, you can attach a few pieces of blue tag, and anyway you make the two gliders have the same mass m, right? Okay, so push the first glider, just push it. So there it's an air track, so no friction. The friction is very small, negligible. So push the first glider and measure the initial speed by using the first light gate. So when the interruption card passes through the first light gate, it will record the interruption time. So the initial speed will be L over T1. L is the width of the interruption card. So during collision they should join together. You can use a small blue tag or small blue tag and a pin. Let them join together and move. So after collision, the speed of both together is measured by using the second light gate, that is V is equal to L over T2. Okay, theoretically, if the total momentum is conserved, initial momentum m into u must be equal to m plus m. They are joined together, m plus m into v. That is m 2m, so they will get cancelled. So u means L over T1 is equal to 2L over the v means 2m. Here m will get cancelled. 2v, v means L over T2. So L and L get cancelled. So it's going to be T2 is equal to 2L. T2 is going to be 2T1. Right. Now we can plot a graph. So we can push the glider at different speeds. You push it randomly, different force apply and push it. So that means you are varying the T1. You are pushing the first glider by at different speeds, means the T1 is going to change. When T1 changes, T2 will change according to this equation if the total momentum is conserved. So we got this equation only when the total momentum is conserved. So you are varying the T1 and you are getting the relevant T2. So according to this, T1 is the independent variable, 2 is going to be the gradient, and T2 is the y-axis. So plot a graph of T2 against T1 practically, and measure it will get a straight line through the origin. Find the gradient of it. Find the gradient of the graph. If the momentum is perfectly conserved, you will get a gradient that is equal to 2. But practically, you might get slightly lower than 2 or greater than 2, whatever it is. If you get exactly 2, you can say momentum is perfectly conserved. Otherwise, if you are getting different values, say for example 1.6, if you are getting, find the percentage difference. Find the percentage difference to give the conclusion. Percentage difference, actual value is 2. You got, for example, 1.6. So 2 minus 1.6 over actual value 2 into 100%. If it is less than 5%, if the percentage difference is less than 5%, we can conclude momentum is conserved in this experiment. Simple experiment to conserve the total momentum. Okay, so this is not in the syllabus, it's in mechanics M2. But anyway, you can use this. Certain other exam boards, they have this equation, Newton's experimental law of impact. That means relative speed of separation. Say for example, you drop a ball. A student wants to measure the E. E is called coefficient of restitution. It's depending on the property of the colliding objects. Say for example, when a ball is dropped from a particular height, so before it hit the table tennis ball, imagine you are dropping a table tennis ball. So before it hits the table, it has a particular speed u. It hits the table at a speed u. After collision, it bounced back at a speed v. So this equation says relative speed of separation means anyway the table is at rest. So relative to table, it's moving away at speed v. So according to this, v is going to be E times. E is called coefficient of restitution, depends on the type of material of the colliding object. So the colliding objects are the table tennis ball and the table, right? So V equal E into relative speed of approach means the speed at which it approaches the table is U, E times U. So V equal E times U, E is always less than 1, right? Perfect elastic collision means E will be equal to 1. That's elastic collision means the total kinetic energy conserved. Normally that we do in unit 4 momentum. Anyway, but V equal E into U. But to measure the V and U experimentally, we can use the law of conservation of energy. That means the ball is dropped from a particular height. So initial height we can measure from what height the ball is dropped. Okay, the initial height we can measure by using a meter rule. So initial height could be measured by using meter rule. So that height, let it be h1. After the bounce, it goes to a particular height, that also measured by using meter rule. You can keep a meter rule in front of it. You can drop the ball. So simple experimental setup. You need a video here. It's easy to measure the height to which it bounced back. So you can keep a setup something like ruler. To ensure the ruler is in vertical, you need a set swell. I already told that. So release the ball initially from height h1. Then after hitting the ground, it moved to a height. I am drawing it separately. So the same diagram, but I am drawing it separately. It moved to a height h2. Initially the height from which it was dropped is h1. After hitting the ground, it's moved to a particular height, that is h2. So these are this is meter rule, right? So 0 of the meter rule should be at the bottom. So 0 of the meter rule should be here. Right. So you can use a video to measure the height to which it bounced back, because at slow motion we can observe the motion easily. We can measure the heights h1 and h2. So the initial height from where it was dropped is u1, so h1. So you can say loss in GP. When it moves down, we neglect the drag force. Loss in GPE equal gain in kinetic energy. So before collision, it has velocity u. So loss in GP mgh 1 is equal to half mu1 square. That's half mu square. That's the speed at which it reaches the table just before collision. So loss in GP equal gain in kinetic energy. It was released from rest. So initial kinetic energy before you release is 0. So gain means final kinetic energy minus initial kinetic energy at which it was released is 0. So from this I could say that u is equal to square root of 2g h1. Okay, so instead of measuring u, I calculated the speed before collision. The speed of approach is calculated. Same way, the speed of separation after collision, it bounced back to a height of h2. That also measured by using meter rule and video at slow motion. Okay, so there we can say loss in kinetic energy after collision leaves the ground at a speed v. So loss in kinetic energy is equal to gain in GPA. So loss in kinetic energy means half mv square, that's the speed at which it left the ground, minus 0 is the speed at the highest point after collision is equal to the gain in GP mg h2. So here V is equal to square root of 2g h2. Right, so U and V we calculated by using the energy equation. Now the equation of the restitution of coefficient says V equal EU. So V equal EU, I'll trace the diagram. So V equal EU means instead of V I can use square root of 2g h2 is equal to E into square root of 2g h1. Square on both sides, so that means 2g h2 is equal to E squared times 2g h1. So 2g will get cancelled. h2 is equal to E squared h1. Okay, h1 is the initial height from where we drop. We can change the initial height from where we are dropping, and we can plot a graph of h1 against h2. h1 is the independent variable, h2 is the dependent variable, and E square will be the gradient. If you plot a graph, you will get a straight line through the origin, that is h2 against h1. It will be a straight line through the origin. Find the gradient. So gradient m is equal to E square. From that, E is equal to square root of gradient. From that we can find the coefficient of restitution. Okay, the next experiment is measuring the density of a liquid by using floating Archimedes principle. So there we can use a test tube, a loaded test tube. The mass of the test tube is capital M, let it be like, but we don't know the mass, capital M, but we can take the mass of the test tube is M. Fill the test tube with a known mass M and let it float in the given liquid. So we should know the length of the test tube inside the liquid, let it be L. If the liquid is not transparent, we can measure the total length of the test tube. If the liquid is not transparent, then we can measure the total length of the test tube before starting the experiment. And we can measure the length of the test tube outside the liquid level. So then by subtracting the length of the test tube outside the liquid from the initial total length of the test tube, we can find the length of the test tube inside the liquid. Anyway, it's not an issue measuring the length of the test tube inside the liquid. Okay, so we know the upthrust is equal to Archimedes principle is weight upthrust when it is floating. Upthrust is equal to weight of the displaced fluid. So weight of the displaced fluid means that is volume of the test tube inside. We take the area of cross section of the test tube. We can measure the diameter of the test tube by using vernier caliper. We can find the area of cross section of the test tube as pi d by 2 square. It's not an issue. We can measure the diameter by using a vernier caliper. Right. Okay. So the upthrust is equal to volume of the displaced liquid. Volume of the displaced liquid means length of the test tube inside the liquid, that is L into area of cross section pi d by 2 square, that we can find. I'll put it as A. So into the density of the liquid rho g, that is the upthrust. When the test tube floats, upthrust is equal to total weight. So total weight is weight of the test tube is m, the added weight is symbol m into g. Okay, so here the independent variable is m. We can change the weight we are putting inside the test tube. We can put different known small weights into the test tube. So m could be changed. When m changes, L, the length of the test tube inside the liquid, also will change. So this is independent variable, this is dependent variable. G and G will get cancelled. So L A rho is equal to m plus m. So make this independent variable. So that is going to we can keep this m as an independent variable. or we can keep L also as an independent variable. Anyway, our aim is to find the density of the liquid. So rearrange it. L is the dependent variable, is equal to divide. Make the always the dependent variable as a subject. So I divide by A into rho, the whole equation. If I divide it by A into rho, so that will become 1 over A rho M plus capital M over A rho. Right. So it is going to be like this is on the y-axis. This is going to be the gradient, because always the gradient should be constant. A is a constant, rho is a constant. So that's going to be the gradient M. The mass added is going to be the x-axis, plus this is going to be the C. This is going to be the y-intercept point C. Okay, so plot a graph of L against the added mass M. So it's going to be y equal mx plus C. So the graph will be a straight line. Find the gradient. So the gradient, that is M, is going to be 1 over A rho. So we need to find the rho. 1 over rho is equal to A times gradient. This M is gradient. A we can find it by using, as I told, A is equal to pi d by 2 square. We can measure the d by using vernier caliper. Okay, so this experiment is used to measure the coefficient of viscosity of a transparent liquid. So they are a ball bearing. Its diameter should be known, should be measured by using a micrometer screw gauge, and drop it and measure the time taken for the ball bearing to move from x to y and y to z. If the time taken is the same, we can say it has reached the terminal speed. If the time taken to move from x to y and y to z are different, that means it not yet reached the terminal speed. So the distance of xy and yz should be known distance. You can measure the length between xy and yz by using the meter rule. With a set square, you can measure the distance xy and yz. Okay, if it has reached the terminal speed and we know the diameter of the ball bearing, there is an equation. It gives the terminal speed is given by Vt equal 2r square g rho O. O is the density of the ball bearing. So we have to use different ball bearings made of same material. They should have the same density. Normally we use steel ball bearings. So, but they have different radius, right? Rho O minus rho F. F stands for the liquid or fluid, or rho L over 9 eta. Eta is the coefficient of viscosity. So the terminal speed we can measure by using, if the time taken to move from x to y and y to, so it's a taller measuring cylinder. We need a taller measuring cylinder. So if the time taken to move from x to y and y to z are the same, we know the distance xy, yz. So we can find the terminal speed by using distance xy over time and distance yz over time. We can find the average terminal speed by using these two terminal speeds. Right, we know the terminal speed. We know the radius of the ball bearing. I told we had to use different ball bearing, but all ball bearing must be made of same material. They should have the same density rho O. Okay, so we need to rearrange the equation. So we are changing the radius of the ball bearing. We had to use different radius of ball bearing. So Vt equal, terminal speed Vt equal 2g rho O minus rho L over 9 eta into r squared. This must be kept in y-axis. The whole thing, this whole thing must be in, it will be the gradient, because they all are constants. G is a constant, rho O is a constant, rho L is a constant, eta is a constant. This must be on the x-axis. So it will be a straight line through the origin. The graph will be a straight line through the origin. That is terminal speed against r square will be a straight line through the origin. Find the gradient of it. The gradient m is equal to 2g rho O minus rho L over 9 eta. So from this, the coefficient of viscosity could be calculated. The gradient will come to the denominator 2g rho O minus rho L over 9m. Right. But there are drawbacks for this experiment. The first drawback is sometimes the height of the measuring cylinder is not enough to provide the, or not enough for the ball bearing to reach the terminal speed. So there is a possibility in the error or uncertainty, error in the systematic error in the value of terminal speed. Then if the liquid is not transparent, you won't be able to see the motion of the ball bearing. So in that situation also, you can't do this experiment. You need a transparent liquid if you want to do this experiment. Okay, so this experiment is used to measure the Young modulus of copper wire, because copper wire is a good ductile or malleable material. So it has reasonably large extension, and the extension could be measured by using meter rule, right? If the wire is made of steel or other materials, we need to use Hooke's law apparatus, but only for copper wire we can measure its extension by using meter rule, right? Okay, so the experiment procedure, without applying any force, the required tension to the copper wire is provided by this weight slot. So initially, without any weight slot, without any tension, measure the diameter of the wire at different points and find the average diameter by using, the diameter should be measured by using micrometer screw gauge, and find the average area of cross section of it by using area is equal to pi d by 2 square, where d is the average diameter measured by micrometer screw gauge. Okay, then attach a known initial, this is used as a pointer. So ruler is kept in vertical position with the support of z square. So the initial position of it should be recorded, where the pointer is pointing on the meter rule should be recorded. Then apply a different, this pointer reading should be taken without any weight slot. Then attach a known weight. The ruler, the wire will extend and the pointer will go down. So by using the difference of the position of the pointer, initial and now, we can find the extension by subtracting, is it? So we can find the extension. So like that, apply different weights, and for each weight, measure the corresponding extension. So, and you can tabulate it, the reading, you can tabulate it, the applied tension or the force and the extension delta x, you can measure it for different weights. Okay, to check whether the wire is within the elastic limit, apply a force, measure the new position, remove the force and check whether it's returning to the previous position. If it is not returning, it's going to pass, or it has already passed the elastic limit. Okay, so you have the force and extension. You know that Young modulus E is equal to tensile stress over tensile strain. So tensile stress equal force over area. Force means the tension. The tension is equal to weight, what we hang here. Then over extension is delta x over x. So we should know the initial length, so that must be measured before you start the practical without applying any force. The initial total length of the wire should be measured, that is x. Okay, so here the variables are the force, that is the weight you apply, and the extension delta x. Rearrange this equation, that is Young modulus is equal to fx over a delta x. So rearrange it, make the force and delta x are the variables. Force is the independent variable, delta x is the dependent variable, but anyway it's not an issue, we can plot other way also, it's not strict. So we'll rearrange the equation like cross multiply EA over x, EA over x into delta x is equal to f. So you can make the f subject, f is equal to EA over x into delta x. So here we plot graph of generally force against extension. So you can plot the graph force. Force means the weight you attached, that is the y-axis, This is the gradient because Young modulus is a constant, area of cross section is constant, initial length is not changing, so that's going to be the gradient M, and the extension will be X. So when you plot a graph, it will be a straight line through the origin. I'll draw the graph here, sketch the graph here. So delta X, and this is the force. Force means the weight we attach here. The graph will be a straight line through the origin. So the gradient, find the gradient. So gradient M is going to be EA over X. From this, we can find the Young modulus. E is equal to mx over A. A is equal to pi d by 2 square. Okay, pi d by 2 square. We can find the Young modulus from this experiment. That same data collection, but we can draw a graph. Here we drew a graph of force against, that is force means the weight we attach against the extension. But we can plot a graph of tensile stress against tensile strength. So there we need to little change the data. This is the raw data what we collected. So we know the initial length and we know the area of cross section. So we can find force over area is the force over area, or tension over tensile stress over area is going to be the tensile, force over area is going to be the tensile stress. So sigma is equal to force over area. Then the strain is going to be extension over original length. So for each reading, we need to measure or find or calculate the tensile stress and the tensile strain for each reading. Dividing the force by area of cross section, we can find the tensile stress. By dividing the extension by area, initial length, we can find the tensile strain. Tensile stress and tensile strain, we know that. So Young modulus is equal to tensile stress over tensile strain. So there it's going to be an equation like this. So this is going to be the y-axis. This is the constant, which is gradient. This is the x-axis. We can plot a graph of tensile stress again, tensile strain. That also will provide a straight line through the origin. Find the gradient. The gradient will be equal to Young modulus. Okay, either way we can analyze the data collected. Okay, so next practical is based on unit 2 waves. Measuring the efficiency of a light bulb. So for that, this is the light bulb. It's a light meter that is used to measure the intensity of light or energy flux or radiation flux of a light. So input power, that's electrical power. Input power is equal to voltage, voltmeter reading into ammeter reading. P equal PI. We should keep the voltmeter ammeter reading constant throughout the experiment. So the input power will be equal to, will be the same. Keep the light meter. Light meter is used to measure the intensity of light at a known distance from the bulb. So the distance could be measured by using meter roll with a set square and draw that I already drew earlier in several experiments. So the light meter must be kept at a known distance. Okay, so the intensity of the light is given by I equal P out. Is it? That's output power of the bulb. P out over the distance square, 4 pi d squared. Okay. So we need to plot a graph. So when the distance changes, intensity is going to change. So we need to change the distance of the light meter from the bulb. For each known distance, we need to measure the relevant intensity. So I is equal to P over 4 pi. E means the output power of 4 pi into 1 over d squared. For different known distances, measure the relevant intensity. So it's going to be on the y-axis. These all are constant, so they will be the gradient. 1 over d squared is going to be on the x-axis. So plot a graph of I against, that is the light meter reading against 1 over d squared. So it will be a straight line through the origin. Find the gradient. So gradient M is going to be output power of the light over 4 pi. So output power of the bulb in the form of light over 4 pi. So P out is going to be 4 pi into M. That's the output power, useful output power. So we need to find the efficiency is equal to useful output power 4 pi M over input power. We found it by using VI, voltmeter reading and ammeter reading. That is input power into 100%. From this we can calculate the efficiency of the bulb. Okay, so measuring the wavelength of light by using diffraction grating. So this is light source, a monochromatic light source. If you have white light and if you want to measure the wavelength of a particular color filter, keep the color filter in front of the white light. Anyway, you can get a monochromatic light. Let the light to pass through a diffraction grating. Exactly behind the light source is going to be the zeroth order. First order, second order, third order, fourth, like that. You will get many orders on the screen. The distance of the screen from the diffraction grating, we must know that is capital D. The angle of diffraction for particular order, say for example when n equal 1, the angle of diffraction is theta. To measure that theta, we need this distance. So I told that earlier in this unit 3, larger the distance of measurement, lower the uncertainty and percentage uncertainty. So we can measure the distance of first order from zeroth order, but instead of measuring that, we can measure the distance of first order from the first order. First order from the first order. Larger the measurement, lower the uncertainty. So we measure the distance of first order to first order by using meter rule. Divide by 2. You will get the distance between the two adjacent, distance between the zeroth order and the first order. If you want to measure the angle of diffraction for the second order, measure the angle distance from second order to second order, divide by 2. You will get the distance from the zeroth order to second order. Right, that way you can measure the distance of first order from zeroth order, second order from zeroth order. You have to measure from first to first, divide by 2, second to second, divide by 2. Right, I already explained that earlier in this unit 3. Okay, so after measuring the distance of particular order from the zeroth order, then I need to find the angle of diffraction. So that's going to be tan theta is equal to that distance. Say this is x I said, so it's going to be x by 2 over d for the first order. For the first order, right? N equal 1 for the n equal 1 angle of diffraction. So take tan inverse. From that you know the angle theta, right? Then we know the equation d sine theta equal n lambda. We should know the d. Normally that you can calculate, you know, normally the diffraction grating, they write it how many number of lines per millimeter. From that we know how to find the d. It's in my unit 2 waves diffraction grating. I put a separate video, there you can find it. So you should know the quantity d. Theta we calculated by using the measurement, already I explained that. Okay, our aim is measuring the wavelength of the monochromatic light. Okay, so here we can for different n, the angle is going to be different. For first order, I explained the by using the diagram how to measure the theta. For second order, we need to measure distance from n equal 2 to n equal 2 divided by 2. Then that distance tan theta equal that distance over d. We can find the angle of diffraction for second order. Same way we can measure the angle of diffraction for third order like that. So when n changes, theta is also changing. So I am going to plot a graph of sine theta again. Sine theta is equal to d is a constant, lambda is a constant. Lambda over d times n. N is actually n is equal to 1, 2, 3 and so on. N equals 0 also we can take, but 0 equals 0, so that won't be a point. So anyway, n equal first order, second order, third order. Plot a graph. This is going to be on the y-axis. This is a constant, will be the gradient. Always when you are plotting a graph, straight line graph, the gradient must be constant. You have to put all the constants into the gradient. This is going to be the x-axis. So plot a graph of sine theta against n. It will be a straight line through the origin. Find the gradient. So the gradient, that is m, is equal to lambda over d. we must know D, so lambda is equal to m times D. From there we can find the wavelength of the unknown monochromatic light. Okay, so the next experiment, measuring the speed of sound by using superposition method. So signal generator gives a known constant frequency AC signal. So for example, if the frequency of the output of signal generator is, for example, 1000 hertz, the both loudspeakers, those are connected to the same signal generator, both will emit sound with the same frequency, which is 1000 hertz. The microphone is kept at a particular distance. Two loudspeakers are very closer to each other. Microphone is at same distance from the two loudspeakers. So the path difference to the microphone is equal to 0. When the path difference is equal to 0, constructive superposition will occur, and the mic on the CRO screen, the microphone is receiving constructive superposition. On the microphone, on the CRO screen, you will see a clear sine wave on the CRO screen. Okay, by keeping L1 fixed, slowly move L2 towards left, and what will happen? When the distance moved by L2 becomes half the wavelength, when the distance moved by L2 becomes half the wavelength from the lambda by 2 from the initial position, what will happen? The path difference is going to be lambda by 2, because initially both have the same distance. Now the distance when L2 moves towards left through lambda by 2, the path difference for the sound reaching the microphone will become lambda by 2. So when it becomes lambda by 2, destructive superposition will occur. So on the CRO screen, nothing will be detected. So the CRO screen will record like this. Then move the loudspeaker L2 further. When it is moved through a distance next lambda by 2, that means when the total distance moved is lambda, constructive superposition will occur, because path difference will be lambda. You will see on the CRO screen, you will see a wave pattern like this. When the microphone is moved further lambda by 2, that is when the microphone comes somewhere here, when the distance from the initial position becomes 3 lambda by 2, again the path difference also will be 3 lambda by 2. Destructive superposition will occur at the microphone. So the wave pattern will become nothing. Detecting this pattern is easier than constructive superposition. So because there is no wave pattern, easy to detect it. So when we move the L2 towards left, whenever the distance moved by the L2 from the initial position is odd multiple of lambda by 2, when the distance becomes equal to odd multiple of lambda by 2, that is when the distance moved to the left, if I say that is D, the distance moved towards left is D. If D is equal to odd multiple of lambda by 2, that is 2n plus 1 lambda by 2, where n equal 0, 1, 2, 3 and so on, then the microphone will detect destructive superposition. You see, the microphone will detect destructive superposition. So from this D, we can measure the distance moved by the microphone, could be measured by using meter rule. So if I make the lambda subject, lambda is equal to 2D over 2n plus 1. N could be these. So when n equals 0, the distance moved is lambda by 2. N equals 0, if you substitute n equals 0, D will be lambda by 2. N equal 1, the D will be 3 lambda by 2. You learn that in waves, when the path difference is odd multiple of lambda by 2, destructive superposition will occur. Okay, so here n equals 0, 1, 2 and so on, right? Integer multiple. Okay. So we know the speed of the sound is given by V equal F lambda. We should know the frequency of output from the signal generator. That will be the frequency of the sound emitted by the both loudspeakers. So that is a known quantity. Instead of lambda, if I substitute 2D over 2n plus 1, that is V. V is constant, F is constant. So D and N are the variables. So we'll rearrange this. So we can rearrange this as 2n plus 1. 2n plus 1 is equal to f over v, 2f over v, 2f over v into d. That is n equal, divided by 2, n is equal to f over v into d you should be able to rearrange. N is equal to, I can, okay, if I want I can write one more step, that is 2n equal 2f over v d minus 1. So n is going to be divided by 2 f over v, both are constants, into d minus half. So this is in the form of y. F is constant, v is constant. We should keep the frequency of output of the signal generator constant. Speed of sound is constant. So that is m. D I am varying x minus c. Plot a graph of n against d. N is the integer 1, 2, 0, 1, 2, 3. N against d. You will get a straight line. That graph will be negative. C is minus half. So it will cut the x-axis somewhere here. Find the gradient. So gradient, so I'll write it here. Gradient m will be equal to f over v. We should know the f, the frequency of output of the signal generator, we must know. So our aim is finding the speed of the sound. Fv is going to be f over gradient. Next experiment. Okay, the next experiment, we are going to measure the speed of sound by using stationary wave. So tuning fork, you know there are a set of tuning forks. There are 7 different tuning forks. They have different frequency. It's marked on the tuning forks. This is a metal pipe. When we keep the practical is, we should initially keep the metal pipe such that its upper opening comes to the surface of water, just immersed completely inside. Vibrate the tuning fork, keep it above it, and slowly move the pipe outside. At a particular length outside that water level, normally it's a water. So when the particular length outside the water level, you will hear a louder sound. That means if you are hearing louder sound, that means a stationary wave is formed. The stationary wave pattern will be such that there is node on the surface of water and antinode is on the open end of the pipe. So since you are moving the pipe from initially it was at the water surface and you are slowly moving out, means first time when you hear the louder sound, the stationary wave formed inside it, it will be fundamental mode. The distance from the surface of water to the open end is equal to lambda by 4, 1/4 of the wavelength, because node to antinode, adjacent node to antinode is lambda by 4. So measure the length of the pipe outside the water level, let it be L. So we can say that L is equal to lambda by 4. So lambda equal to 4L. Like that, repeat the same experiment for different tuning forks. For the known frequency, we know the frequency of the tuning fork. So whenever we start, when we use another different tuning fork, we have to keep the upper end of the pipe inside the water, and we have to pull it out slowly until we hear a louder sound, right? So every time the procedure is the same, right? So lambda equal 4L, V equal F lambda for one of the traveling waves. So that is F into, instead of lambda we can put 4L. So we can plot a graph of 1 over L is equal to 4 over V into F. So this is going to be y-axis. This will be the gradient, which is constant, and this is the x-axis. So when you plot a graph of 1 over L against F, it will be a straight line through the origin. Find the gradient of it. So gradient M is equal to 4 over V. From the speed could be calculated by 4 over gradient. Okay, so here you are given a constant frequency electrical vibrator. That means the frequency of vibration of the electrical vibrator is constant, but we don't know what is its frequency of vibration. We have to find that frequency of vibration. So what can we do? We can complete a setup like this. We are going to create a stationary wave in the string from the pulley to the electrical vibrator. So the mass is used to provide the required tension on the string, and we know the equation for transverse wave on a stretched string is given by V equal square root of T over mu. So T is equal to mg. The attached weight gives the required tension. Okay, so in this experiment, it's like this. We are going to create always for a given known mass, attach a known mass, maybe 50 gram or something like that. Attach a known mass. Keep the electrical vibrator closer to the pulley. So let the electrical vibrator vibrate. Initially keep it closer to the pulley and move it slowly away from the pulley. So the L will increase. The length of the string from the pulley, the effective length, that is length of the string from pulley to the electrical vibrator will increase when you move the electrical vibrator from pulley towards left. So the L will increase. When the L increases, for a particular speed, V equals square root of T over mu, we attach a known weight. So for a particular speed, there will be a fundamental mode of vibration. So when you see a fundamental mode of vibration like this, between the pulley and the electrical vibrator, so this is, we can call this name, this length is L, node to node, that is equal to lambda by 2. So we can say lambda by 2 is equal to L. So lambda equal 2L. Right. So one of the transverse wave, there's a traveling wave, it reflects and overlaps and it forms the stationary wave. See my video related to stationary wave. So V equal F lambda. So that is F into, instead of lambda we can say 2L, where V is equal to square root of T over mu. T means that is the tension, which is equal to mg. Okay, so m we can put, instead of T, that I can put mg. So that's going to be mg over mu equal F into 2L. Square it both sides. So that is mg over mu is equal to F squared times 4L squared. So the variables are L and M. I can vary the mass. Every time I'm going to change the attached mass, that means I'm going to change the tension. Then again I bring this electrical vibrator closer to the pulley and I move it away from the pulley such that again a stationary wave is formed, fundamental mode of stationary wave. So every time I am going to change the mass, so I can increase the mass gradually, start from 50, then 100, 150, 200, or we can say 20, 40, 60 like that. I can increase the mass attached it, that is I am increasing the tension. Every time I am creating a stationary wave, that is fundamental mode of vibration. Fundamental mode means the string will appear like this. So the L is going to change when M is changing. So I can rearrange the equation like I can put the M as subject. So M is going to be, M is equal to F mu F squared. I can draw a graph. I can keep either M as a independent, but actually practically I'm changing M, that changes the L. So M should be the independent variable, L should be the dependent variable. So I can keep L squared on the y-axis. So L squared is going to be L squared equal to G over 4F squared mu, 4F squared mu into M. I think I am correct, is it? L squared is equal to G over 4F squared mu into M. So this is going to be on the y-axis. This is going to be the gradient. This is on the x-axis. Plot the graph of L squared against M, where every time I am getting fundamental mode of vibration. By changing the M, the practical, we have to keep this close and move it away until fundamental mode of stationary wave pattern is seen. So you will get a gradient. So the gradient, M is the mass attached here, right? That provides a tension. So the gradient, that is gradient, that also M, careful that M and this M are different. The gradient M is equal to G over 4F squared mu. I need to find the F. So from this, you can find the F. Is it? You can make the F subject. So F squared is going to be G over 4mu. So F is going to be square root of G over 4m mu. mu is the mass per unit length. That we can measure mass per unit length of the string. We can measure the length of the string. We can measure the mass on a digital balance. Divide the reading of the digital balance by the length of the string. We will get the mass per unit length of the string. That is the mu. From this we can find the frequency of vibration of the electrical vibrator. So here we are not changing the frequency because a fixed frequency for that particular electrical vibrator. We measured that particular frequency. Okay, so this is the photoelectric effect experiment. So here a photocell color filter is used. Electromagnetic white light is allowed to fall on it. So this is white light. So we can draw the white light here. The white light falls on it. Normally in the color, on the color filter, the wavelength or the frequency of the light that is going to pass through it is written there. We know the experiment. So the electrons are released and electrons are collected by the collecting electrode, and there will be a picometer reading. This is called opposing voltage or negative voltage. Keep the initially opposing voltage at 0 and gradually increase. Opposing voltage will try to attract the emitted photoelectrons towards the emitting electrode. So when you increase the opposing voltage at a particular voltage, the picometer reading will become equal to 0. That time note down the voltmeter reading, that is called stopping voltage. So when the picometer reading becomes 0, we can say all the electrons emitted from the emitting electrode is stopped. So that means we know the equation for photoelectric effect. Einstein's photoelectric equation is given by HF, that's energy of the photon. HF equal phi is the work function plus half mv squared or kinetic energy of the fastest electron. So when the electron is stopped by the opposing voltage, the electron is losing all its kinetic energy. So loss in kinetic energy, that is loss in kinetic energy of the fastest electron, is equal to work done against electric potential. Work done against electric potential is given by W equal QV, Q or E. This is electron, so charge of electron is simply, we can say E into stopping potential. The voltage at which the picometer reading becomes 0 is the stopping potential. So when I combine these two equations, I can write HF equal phi plus Q Vs. Okay, so if we know the frequency of the light passing through that, if the wavelength is written there, we will be able to know the frequency by using C equal F lambda. We can calculate the frequency of it. Or instead of frequency, we can use a wavelength, whatever it is. Different arrangements we can do. But the variables are, we can change the different color filter, means we are changing the frequency. So the stopping potential will change. So Vs is going to be the subject. Vs is the y-axis. Vs is going to be H over Q into F minus phi over Q. You should be able to rearrange it. So the variables are, frequency is the independent variable because when we change the color filter, the frequency of the light passing through that also will change. That is the independent variable. And Vs is the dependent variable. So this is on the y-axis. This is going to be on the it will go into the gradient because H and Q are constant. This is the x-axis minus C. So when you plot a graph of stopping potential against frequency, it will be a straight line, but it will cut the x-axis like this and it will pass through that. This is going to be the threshold frequency. If you find the gradient of it, from the gradient, we can find gradient M is going to be H over Q. If we know the charge of the electron, we can find the Planck constant. Also, by using this graph, we can find the frequency of unknown light if the frequency is above the threshold frequency. So we can have a color filter, just keep it on top of this, and we don't know the frequency of the light, white light. When it passes through that color filter, the light will become the same color. We don't know the frequency of that light passing through the unknown color filter. We can find its frequency. After plotting this graph by using the known frequency of color filters, now you keep the unknown frequency of color filter on the glass through which the light is passing through the emitting electrode. Now adjust the stopping point. I just vary the voltage until the peak power meter reading becomes 0 and measure the stopping potential. So you know the stopping potential for that particular unknown frequency of light. So if you know the stopping potential, use this graph and find the frequency. From that you can find the frequency of that particular unknown color light, monochromatic color light. Okay, next thing is measuring the electricity practical. There are two standard practicals. Measuring the resistance of a given test wire, normally nichrome wire or whatever it is. The test wire is connected across these 2 points. So complete the circuit. Voltmeter reads the voltage across the length L. So complete the setup. Ammeter reads the current through it. Voltmeter is an ideal voltmeter, no current flow through it. So you touch this pointer P, at a known distance from the left end of the given test wire. When the length L is known, the voltmeter reads the voltage across it. So we know that voltmeter reading divided by ammeter reading. Ammeter reading is the current flow through that particular wire. So voltmeter reading divided by ammeter reading that will give the resistance of the wire of length L of the wire of length L. So this length, the voltage is voltmeter, ammeter reads the current. So we know the resistance by dividing the voltmeter by ammeter reading. So R is going to be rho L over A. A we can measure by using micrometer screw gauge, measure the diameter at different points, different orientation, find the average diameter. So A is going to be pi d by 2 squared. Okay, so you are going to touch the given wire at different known length, and each time you are going to measure the resistance. So L is the independent variable, R is the dependent variable. R is going to be rho over A times L. Plot a graph of R against L. The gradient will be rho over A. So when you plot a graph L, this is R. The graph will be a straight line through the origin. So gradient will be rho over A. From that you can find the resistivity. Rho is equal to gradient times area of cross section. Okay, the last practical, measuring the inter resistance of a power supply or cell by using this circuit. Voltmeter reads the terminal potential difference. Ammeter reads the current flowing through the cell as the variable resistor. So this the practical is when we change the RV, the current flow in the circuit will change, and we know the equation for the current flow in the circuit will change. We know the equation for terminal potential difference of the cell, which is read by the voltmeter, equal E minus IR. So here the possible variables are I and V, because EMF we should keep constant. So when you are doing practical, only when you are taking reading you have to switch on, otherwise you have to keep the switch off, right? So I we should change by changing the value of RV. According to Kirchhoff's second law, when I change the RV, the total resistance of the circuit will change and the current flow will change. Okay, by changing the RV, we can record the voltmeter reading, that is V. So V is equal to minus R I plus epsilon. So we'll plot a graph of terminal potential difference, that is the voltmeter reading, against the ammeter reading. So this is going to be the gradient plus C. So when you plot a graph, the graph will be y-axis V, this is A, yeah. Then find the gradient. So the gradient will be, this is if you start from 0, this is going to be y-intercept point, that will give the EMF of the cell. So find the gradient, negative gradient equal negative R, so gradient will be equal to R. Okay, normally they ask why should we use this resistance, because when we are changing the RV, accidentally it could become very low, then the current flow could become very high. It can damage the cell when the current flow becomes high. For the safety reason of the cell, we use a low resistance, somewhere around 20 ohms is enough for the protection. Okay. Okay, next, the last topic in this Unit 3 video is about graphs. Normally when we plot graph, you know how to plot graph, but try to use at least 60% of the grade. It's not necessary to start from origin. Depending on the data given, it's not necessary to start from origin. But try to scale such that 60% of the grid is used. When we are scaling, we don't normally scale like for example 0, 3, 6, 9, we don't scale, or we don't scale normally 0, 7, 14 like that, we don't scale normally. So normally the numbers that could be scaled when you whether x-axis or y-axis, it could be something like, it's not necessary to start from 0, it can be start from any number, but even the intervals could be something like 1, 2, 3, 4 or 0 0.1, 0 0.2, 0 0.3, 0 0.4, or even it's like a 0 0.0010 like that we can continue, or it could be 10, 20, 30, 40. Like that only we normally scale the graph, or maybe something like 5, 10, 15, 20 or 10, 20, 30, 40. Those are the normal scale we use. Generally we don't scale like 3, 6, 9 or 7, 14 like that. We don't scale very unusual numbers, we don't scale it. But anyway, you have to use generally 60% of the, at least 60% of the grid must be used. So you have to scale according to get 60% of the grid is used for your graph. When you are drawing graph, first you should think about, you must name the axis with the names. If the given units on y or x has units, you have to show the units and you have to name it. Maybe this is length, this is mass. What I'm just writing mass. You have to put whether it's in kilogram or this is in meter. You must show that. Okay, so that's very important. And when you are plotting the values, better show clearly the cross. Don't use dot. It won't be clear. Put a cross clearly. Put a cross clearly, right? And best fit line. Best fit line means this is best fit line. So that's very common mistake students they have. Best fit line does not mean it should pass through all the points. Maybe this is not a best fit line. Maybe a line, I draw the line first. So there are points something like this. Right. This is not a best fit line because it's passing through many points, but the points, those are not on the line, they all are on one side. This is not a best fit line. So the best fit line means the points, those are not on the line, should be on either side. Maybe something like this. This is the best fit line. So there are points on the line. At the same time, there are points not on the line. They are almost equally on either side of the line. This is the best fit line. So second one is the best fit line. This is not a best fit line. Okay. So consider that also when you are plotting graph. You have to name the axis. I already told that. Units you have to put it. Next, when you are finding gradient, don't use the points already you put on the graph. Use some other points. Say for example, some other point from the line. Don't use this point or this point already on the graph. You can use just a point which is not part of the data and take a point. Take reasonably larger distance, the points, and show a right angle triangle. Show a right angle triangle like this when you are finding the gradient. If you want, you can extend the lines until they come to the x-axis and y-axis. So it will be clear which points you have taken to find the gradient. Better you show the right angle triangle when you are taking the gradient. Also, when you find the gradient, you should show the unit of it. Say for example, the gradient here, if it is for example, this is speed or something like that, the unit is meter per second. This speed just time, something I'm saying time, it's in second, means the gradient, the unit when you find gradient is equal to, you will get a value, but show the unit of the gradient also. Meter per second divided by second. So meter per second square. Show the unit of the gradient also. Yes, you must know these things. I already told that you don't need to start from 0. You can start from some other point. If you want, you can start from something like say 10, 15, 20, 25. This could be start from 2, 4, 6, 8 also. So depending on the data and such that you use 60% of the graph, you can scale it conveniently, but it's not necessary to start from 0. Right. That's all regarding this unit 3. It's a big video. I hope it will be useful to you. You can pass your comments. Right. Bye.